Hello and welcome to our course on blockchain and Web3. Blockchain is everywhere these days, and it's not going anywhere anytime soon. It's bringing in massive new investments, new opportunities, and could bring about a new version of the web. With this course, we want to understand the most important concepts in blockchain and Web3. We're going to build a mental model of the Web3 space so that we can make better decisions when working with all these new technologies. So what does the course cover? In the first half of the course, we'll work on our foundation. We'll really understand what blockchain is and how it works. We'll learn about immutability, decentralization, and distributed networks. We'll look at Bitcoin, the blockchain that popularized the whole idea. We'll use Bitcoin as an example in our investigation of how blockchain works. And then we'll go into how Ethereum and other blockchains expanded on the initial ideas of the blockchain. Because Web3 is new and blockchain is an emerging technology, the topics we're covering will change quickly. There's also lots of attention being paid to these things in the media, and there's a lot of poor information going around. But I'll give you a secret. The best way to get ahead when a technology is surrounded by hype, change, and volatility is to stick to the fundamentals. These are the things that don't change. As an added bonus, this approach also helps to future-proof this course. If you understand the fundamentals well, most of the changes that we'll see in the future are just minor details that you can learn if you ever need to. In the second half of the course, we'll look at the applications of blockchain that make up Web3. We'll learn how blockchain is evolving, and we'll look at some of the main ideas in this new emerging web, discussing topics like smart contracts. This is code that runs on the blockchain, and we can't talk about smart contracts without talking about DApps, or decentralized applications, and how we can use the blockchain to build them. There's a topic of much debate: NFTs, or non-fungible tokens. Do we really need them? How do they work? And why are they so expensive? And we have DAOs, decentralized autonomous organizations. Will they replace the giant corporations that dominate the web today? There's so many of these acronyms being thrown around left and right nowadays, it's easy to get lost. We'll dig into each of them, look at examples, and understand the most important concepts. In this later section of the course, we'll look at things with a slightly more critical eye to see what makes sense and what doesn't, to avoid making some very common and very costly mistakes. For example, when investing our own time and money into cryptocurrencies. Now, these are just some of the topics that we'll cover in this course. I want you to be able to cut through all that hype, all those scams, and all that marketing to really understand how things work whenever a conversation about blockchain comes up. As always, know that nothing in this course is financial or investment advice. The goal and focus here is to lay the groundwork for you to understand the world of Web3 and blockchain if you decide it's something you want to dive into. This course should empower you, giving you tools for understanding that can help you navigate and prepare for possible future developments in the web. It should give you some understanding to avoid scams, get a job in the space, or even just to educate your friends. All right, without further ado, let's dive in to the exciting world of Web3 and blockchain. All right, here we go. Jumping straight into our big question. What is Web3? Well, Web3 is a vision for the internet. It's a World Wide Web that's based on blockchain technology. We'll dive into exactly how blockchain works in just a moment. We'll even go into why so many people are hyped up about the potential of Web3. There's a lot of money being poured into these cryptocurrencies. Why is that? We'll get into it. But first, it'll help us to get a little bit of a history lesson on the current web. How did we get to Web 3? What about Web 1 and 2? Why do we need a third version of the web? The story starts in the early 1990s. This is when the internet started taking off and began being adopted in households by regular people instead of mostly being used by governments and universities. The amount of users that could access the internet was about to start increasing very quickly. This early internet started off with groups of communities that often shared common interests. Check out this website from 1995. Back then, the internet had different applications as well. If I was interested in Star Trek, I could communicate with other Star Trek fans on forums that lived on Usenet. This Usenet was a globally distributed, decentralized network of discussion forums. It was mostly run by a community of users. Notice these words like decentralized and globally distributed that apply to both Web 3 and this early internet. But hold on, we're not at Web 3 yet. What we're describing is Web 1.0, where we had companies like Yahoo and tools like Internet Explorer and Netscape Navigator. With these tools, we could share information with each other, but once something was published, it was pretty static. Most of the web, like we just saw, was these static HTML pages. They wouldn't change or interact with you. The web was basically read-only. 15 years passed, and by the year 2005, this idea of Web 2.0 started to gain more and more popularity. This is the internet that we're all familiar with. We got applications like Facebook, Netflix, and YouTube. Web 2.0 was a more interactive web that focused on user interfaces that both looked good and were easy to use. As things got easier to use, pretty much everyone, including parents and grandparents, started using our internet. The focus became on content generated by users. We could now read and watch data that was published, but also create our own data and publish it to these giant platforms like YouTube. The beauty of this was that we could all now participate in what was happening on the internet. But, and there's always a but, things became centralized in these internet giants. The current internet is dominated by the Googles, the Apples, and the Microsofts of the world. So things became more usable as the internet spread to our phones, our laptops, and TVs, but this came at a cost. The loss of power of the individual. Users like you and I don't have control over our own data. We don't really know how it's stored or what happens to it when it goes to these platforms. Have you ever heard the phrase, if you're not paying for the product, you are the product? Think about it. If the product is free, you are the product. What this means is if you have a company or a website that's working hard to deliver content to you without asking for some payment, they're probably using the data you're giving them, both directly and indirectly, and selling it to advertisers and other interested parties so that they can make their money. Take Facebook, for example. The company has spent millions of dollars into developing their site and keeping it running, but they've amassed a wealth of billions of dollars by allowing advertisers to target specific users with specific ads. This is the prevalent business model of the current internet. Now, this doesn't apply to all sites, but the point is, it's impossible for you to know for sure exactly what these sites are doing. You have to put your trust into the privacy policy of the company. You have no way of seeing what actually happens behind the scenes. In fact, some of these internet giants have gotten so large, it's likely there's no one person even inside the company that understands how everything fits together. In response to this internet that's run by monolithic, multi-billion-dollar companies, around the year 2020, Web 3.0 started gaining traction. The idea with Web 3 is we'll have decentralized applications that live on the blockchain. The community will once again be in charge of running the applications and organizations that make up the internet. Kind of like those discussion forums we had on Usenet back in 1995 and earlier. There will be no need for these giant corporations that own centralized platforms with millions and millions of users because we'll be able to interact with each other on the blockchain directly. One of the big goals of Web3 is to challenge the dominance of these giant companies and their platforms. Just like in Web 1.0, the internet will be decentralized once again. At the same time, we'll keep the interactivity of Web 2.0 with the addition of some added security and transparency. That's the Web3 vision. All of this will be based around blockchain, this technology that was originally introduced all the way back in 1991, but only really started gaining attention in 2008 when someone named Satoshi Nakamoto introduced Bitcoin. So how exactly would all of this work? What's so special about Bitcoin? Will Web3 succeed in its goals? We need to start by learning a little bit more about blockchain. And on that note, I'll see you in the next video. Welcome back. Blockchain could help us bring about this next generation of the web. But how? What exactly is blockchain? Let's dive straight in. Blockchain is, well, it's a chain of blocks. This chain of blocks forms a database. Each block is a record in the database that stores some data. These blocks are linked together using cryptography to keep the database secure. Let's break it down by looking at a single block. It'll be made up of three main things. We have some data that's stored in the block. For now, let's just say it's data on popcorn. Alongside this data, we would have a hash of the current block that uniquely identifies the block and everything it contains. The hash is a string of letters and numbers that acts like a fingerprint. Just like a person's fingerprint is unique only to them, a hash is unique for every possible block. If we change the data to, say, ice cream, the hash of our block will change as well. Because of this feature, hashes are a very useful tool for detecting if something has changed. Finally, we have the hash of the previous block, or the fingerprint of the block that was added to the blockchain immediately before the current block. It's this previous hash here that creates the link between blocks that forms a chain. Let's take a look at an example. Say we have a blockchain with just 3 blocks. Each of these blocks, as expected, has a unique hash. In the example here, I'm using these shortened, abbreviated hashes to keep things simple. So we have 3 blocks, each with a unique hash, and a link to a previous block, using a hash which points to that block. Now, the first block here is special. It came before all the others, so it doesn't have a previous hash. In blockchain, this is what is known as the genesis block, the one that starts the whole chain. Now notice that the links between blocks are created by having the previous hash of the second block here point to the hash of the first block. And it's the same for the 2 other blocks. The beauty of this approach is that now, if a hacker tries to go into the blockchain and change the data in one of the blocks here, well, when the block changes, the hash here will also change. Now, the link with all of the later blocks will be broken because the previous hash no longer matches the hash of the hacked block. The consequence of tampering with just one block means that all of the blocks after it are invalid. The chain has been broken. Now, this might not seem like the best behavior. We don't want hackers to be able to break the entire blockchain, right? We'll see why this is in fact a feature and not a bug in the next video. But first, let's recap. So, blockchain is a database, but it's a database that has some special rules. Just like any database, we can read existing blocks and make use of the data they contain. We can add new blocks and connect them with the chain, but we can't update existing blocks. That's not allowed. This is a property of the blockchain known as immutability. Once a piece of data is on the blockchain, it's there forever. You could later add some new data in another block that changes the current state of your data, but the original will always stick around. Now, because part of what our blocks contain is the hash of the previous block, immutability means that we can't remove blocks from the blockchain either. Say we wanted to remove this third block. Because the fourth block is immutable, we can't change the previous hash that it points to, which means the blockchain will always expect that third block to be in the chain, exactly like when it was originally added. That's immutability. And it's how we use these hashes from the world of cryptography to create a chain of blocks. There we go. Finally, we have a picture of how the blockchain actually looks. In the next video, let's explore the other key feature of blockchain, the fact that it's distributed. After that, we'll be able to look at some really cool applications of this technology. It'll be a good one, so I'll see you there. Welcome back. In this video, we'll explore the other half of what makes blockchain so special. We know that blockchain is immutable. Once something is added, it can't be written over or changed in any way. But all on its own, immutability isn't so special. The other most important feature of blockchain is that it is distributed. This is a really cool concept. The blockchain is stored on a network with many computers all across the world. Each of them contains a full copy of the entire blockchain. When a block is added to the blockchain, it's sent to all the other computers on the blockchain as well. Because we have all these copies, the data on the blockchain is not under any one person's control. It's distributed. But there's a challenge with keeping track of so many copies, which is that each of these computers could potentially disagree on the current state of the blockchain. To deal with such potential disagreements, we have what's called distributed consensus. Consensus is a way of getting agreement across the blockchain network. We need this agreement so that if someone asks, "What's the latest true state of the blockchain?" well, we can give them the one true answer that's shared by everyone. Let's take one more look at what happens when we add a block to the blockchain. At first, this is done on one machine. When that block is fully formed, it's sent to all of the other computers or nodes in the network. Each of these other computers here validates that block to make sure that it follows all of the rules of the blockchain. For example, when they recompute the hash of this block, they check to see that it matches what was sent them. If it doesn't, they just don't add that block to their copy. So what's the consensus part? The process of determining consensus means that a majority of the computers on the network need to agree on the latest current state. To be exact, that means that at least 51% of computers participating need to agree. If they do, there's consensus, and that block is finalized. This is the new true state of our blockchain. And if some node on the network is acting maliciously, well, because everything on the blockchain is visible to everyone, they can be flagged and punished, or removed from the network entirely. Let's go back to our example when a hacker tries to change a block for their own malicious purposes. Changing anything related to the block would result in the hash of that block changing as well, which then makes the previous hash of the next block invalid, which breaks the entire chain after the hacked block. This would be a problem if we weren't distributed, allowing hackers to break our entire database by corrupting the data in one of the blocks. But with a distributed blockchain, we now have many copies of this data. Say one of the copies lives on a computer that's run by a hacker, who then changes a previous block for their own benefit. Before that change is applied across all the computers with their own copies, it would need to be verified first. We would need consensus. Unless the hacker could somehow gain control over 51% of all the computers in the network all at the same time, well, their change would basically just be ignored. While this type of 51% hack is theoretically possible, this would be extremely expensive to accomplish. Probably even more expensive than any benefit that it would give to the hacker. And even if hackers did gain control over 51% of the blockchain network, they wouldn't be able to destroy old blocks. They would only be able to verify changes since they gained control, which means that in the worst case, as long as the hackers are eventually caught, we could roll back the state of the blockchain to before they gained control. So that's one of the advantages of blockchain, that it doesn't require trust. We don't need to trust everyone who joins the network because we instead rely on consensus. All right, so consensus allows everyone to agree. But why deal with all of this in the first place? Why is being distributed a good thing? Well, a centralized database that lives in one location or on one computer has a single point of failure. If that one database gets corrupted or hacked or loses power, you lose access to the entire system. Instead, if you remove the need for any centralized system, everything becomes a lot more resilient to failure. The data is distributed, which means that if one of the computers runs into a problem, there's still many other copies of the data available. And because anyone can view the data, it's also more transparent. We don't have to trust a central authority on what the database actually contains, and that's even if the central authority was willing to tell us. Blockchain being distributed is what allows us to say that it's decentralized. When you have a system that's distributed and there's no central authority that's in control of it, you have a decentralized system. With this understanding, we can start diving in to how blockchain is used, why it's being used, and what the advantages and disadvantages of it are. The pieces are starting to come together. In the next video, let's look at one of the many possible applications of the blockchain. I'll see you there. Here we go. At this point, you've probably asked, what data does the blockchain actually store? All of this theory is nice, but how does it actually work in practice? The truth is that there are many different blockchains that exist, and the data they store depends on which blockchain we're talking about. Let's use the Bitcoin blockchain as an example. In case you've been hiding under a rock, Bitcoin is what popularized blockchain. We have the Bitcoin blockchain that's used for sending and receiving a digital currency known as Bitcoin. We'll talk about other cryptocurrencies and dive a little deeper in a later video. But to be clear, Bitcoin is both a blockchain and a currency that uses that blockchain. This distinction will be important as we learn more about the different applications of blockchain. All right, moving along. Bitcoin is used for financial transactions. Like any currency, we need to know where the money is coming from, who it's being sent to, and of course, the amount that's being sent. BTC here refers to the Bitcoin currency, just like USD refers to American dollars. So with Bitcoin, a block's data contains a group of these transactions. That's exactly what the blockchain stores. Kind of like a spreadsheet that keeps track of how the currency is moving around from person to person. Just like spreadsheet files, blocks keep track of the latest transactions that are going to be saved on the blockchain. But remember, blocks are immutable. Once they've been added to the blockchain, they can't be changed. So how do we add transactions? Well, it's when a block is being created that we can add transactions to that block. But creating a block requires validating that those new transactions being performed are valid. For example, if Elizabeth is sending Bitcoin to Ripley, she needs to have the amount of Bitcoin that she's sending in order for the transaction to be valid. This process of creating and validating a block is hard work. So, to motivate people to help out with block creation, the person who makes the block gets rewarded with a small amount of Bitcoins for themselves. This process of rewarding people for validating transactions is called mining. Mining because it introduces new resources into the blockchain, just like mining for gold introduces new gold into our economy. So how are these transactions added to an immutable blockchain? When the block is filled up with transactions, those transactions are saved into that new block. Everything is fully verified, and that block is added to the blockchain. Those transactions are now settled forever. Think about that. Each block can have hundreds or even thousands of transactions. And because we have groups of transactions that each live in separate blocks, our data is distributed across the entire blockchain. Each block only contains part of the history of the blockchain. The most recent block will always include the most recent transactions. That's how the whole thing is broken down. Now, don't just take my word for it. There are many sites that allow us to navigate the real-life Bitcoin blockchain online. And that's exactly what we'll do in the next video. I'll see you there. Welcome back. Let's poke around the real-life Bitcoin blockchain. Because the Bitcoin blockchain is distributed and readable by anyone, there are many sites that allow us to explore it online. One such site is the Blockchain Explorer. This site allows us to browse here on the left the most recently mined blocks. These are the blocks that were just added. And here on the right, we see the transactions that are soon to be added to a new block. These are called unconfirmed transactions. They haven't been fully verified yet. But it's pretty awesome seeing these transactions scroll by in real time. Every once in a while, you'll see some transaction worth millions of dollars. That is, millions of dollars worth of Bitcoins. And you can see exactly where it's being sent to and from. This is pretty cool. So we can click into any of these blocks, any block that was added to the blockchain, or look into one specific transaction. To start, Let's dig into one of these most recent blocks, say the third most recent. We can see exactly when this block was mined or added to the blockchain. There's the miner's reward of 6.25 bitcoins, which were awarded in response to verifying 2,150 transactions, all on this single block. Let's scroll a little further, where we can see the hash that's used to find this block on the blockchain. Check it out. Just like we discussed, we can see that a block is about 1.5 megabytes in size for Bitcoin right now, and that in total, there were over 50,000 Bitcoins sent to and from different accounts as part of the transactions logged in this block. The transactions that we can see by scrolling further down. The first transaction in a block is known as the Coinbase. It contains the newly generated coins that are given to the miner, the block creator, as a reward for their work. We see the amount here is slightly more than the 6.25 we discussed earlier. Why is that? Well, if we scroll up, we can see that there is an additional 0.11 Bitcoin worth of fees paid by everyone who did a transaction on this block. And we can see that the Coinbase transaction was sent to this ID here. This ID corresponds to the address of the miner. Specifically, it corresponds to an address that points to what we call the miner's wallet, where a wallet is where these Bitcoins can be stored. Blockchain transactions always involve the wallet address of the sender and the wallet address of the receiver. That's all we know. Notice that here with Bitcoin, even though we have the addresses of everyone who's both sending and receiving Bitcoin, we don't have their names or any personally identifying information, but instead, we have just these anonymized addresses, these strings of letters and numbers. We can click on this address to see what information we get, but all we learn about this address is what's already on the blockchain, which means we can see any and all transactions that were sent involving this address, and we can see the amount of Bitcoins that were both received and sent. To get the current amount available at this address, we can subtract the sent from the received, and we get that final balance. Both wallets and addresses are really important concepts when it comes to blockchain. So we'll spend our time both in this video and a future video really understanding them. Now, before we move forward, let's take a fun little break. How do we split a Bitcoin? So far, we've been seeing Bitcoin amounts that look something like this. We have a whole number followed by 8 decimal places. Because Bitcoins have increased in value so quickly since they were created, there's a need to divide a Bitcoin into smaller units. The smallest, with all zeros and a 1 in this last decimal place, is 100 millionth of a Bitcoin. This is known as 1 Satoshi, after Satoshi Nakamoto, the creator of Bitcoin. In other words, we have 1 Bitcoin being equal to 100 billion Satoshis. When talking about smaller amounts of Bitcoin, it's often easier to talk about Satoshis as opposed to these very tiny fractions of a Bitcoin. There you have it. Bitcoins are divided into Satoshis. And now, back to Blockchain Explorer. Now, there's something strange that you might have noticed. If we go back to our list of transactions, let's see what other information we can find. For our Coinbase transaction, that first one on the block, we have a transaction hash, just like we had hashes for our blocks. We have the address of the wallet that this amount of Bitcoin here was sent to. We have a timestamp, and we have this op return, which just means that the Bitcoins are going both to and from this wallet here. But let's take a look at the second transaction on the block. We now have a fee here that was paid by the sender in order to use the Bitcoin network. This fee is sent to the miner here as a reward, again included in that 6.36 Bitcoin. But now we have a valid sender's address, and actually we have two addresses that are receiving this currency. What this means is that the 1.7 Bitcoin that lives in this address is being split between this first address and the second. Notice that this second address is exactly the same as the sender, because all of the Bitcoin in the address needs to be accounted for. So we have part of the total being sent to a new address and part of it being returned back to the sender. We now know that with Bitcoin, transactions can have multiple recipients, but also multiple senders, believe it or not, which would mean that the Bitcoin is being pooled together from multiple wallet addresses. Let's find an example. I've gone ahead and found a transaction not on this first page, but on the fourth page of this block, where we've sent 3 Bitcoins pooled together from 2 different addresses and being sent or being split between these 3 recipients. What a transaction! This is happening all in one go. 5 addresses are involved in a single transaction. What's up with that? Now that we've had a taste for how the Bitcoin blockchain looks in real life, we'll explore why addresses and transactions are so important to the blockchain in the next couple of videos. I can't wait, so I'll see you there. Blockchains are distributed ledgers. This is something you'll hear a lot in the blockchain world. But what does it mean? So far, we've looked at the blockchain and seen that it is distributed, with many copies of the entire blockchain existing on computers around the world. We've also looked at transactions and used Bitcoin as an example. Now, we know that blockchain is distributed, but what's a ledger and how can it be distributed? To really break it down simply, blockchain is most often used as a way of tracking ownership. For example, in Bitcoin, we track who owns how many Bitcoins. The data that we store on the blockchain are transactions that transfer ownership from one person to another person. So, we can look at the blockchain as just a giant spreadsheet of transactions between people. Now, when you think of a store, a business, or even a large government, who is really good at keeping track of transactions? It's the accountants, the bookkeepers. Blockchain takes advantage of 2 key ideas from this world of accounting: a journal and a ledger. A journal is a detailed account of all the financial transactions of a business. When any transaction is made, a bookkeeper enters that transaction as a journal entry. The transaction could be a sale, a purchase, or even just moving cash around. If it affects one or more business accounts, the journal entry will include the accounts that are involved. So the journal is like a basic log, containing sequential records of how money is flowing into and out of the business. On the other hand, a ledger keeps track of every financial transaction as well. But instead of sequentially, transactions are organized by account and by type. You'll usually see ledgers split into things like assets, liabilities, revenues, and expenses. Now, this part is important. The ledger will keep track of the total balance in all of those accounts. So, transactions are first recorded in a journal, and then second, organized into a ledger, which includes account balances. Okay, that's the boring accounting stuff. Now, remember how blockchain stores transactions in blocks and pretty much nothing else? Well, that's exactly what a journal is. A database of transactions. Blockchain is perfectly suited for storing financial transactions, just like an accounting journal. It's the block creators or miners that are the bookkeepers, saving any new transactions to the journal. What about the ledger? I thought blockchain is a distributed ledger and not a journal. Let's find out what makes blockchain a ledger in the next video. When we're done, we'll have a much better understanding of how blockchains work under the hood. I'll see you soon. What makes blockchain a ledger? How do blockchains keep track of total balances? This is interesting stuff because we're coming to a point where different blockchains behave differently. So far, we've seen that a blockchain is perfectly suited to store a journal of transactions. But blockchains are called distributed ledgers, and ledgers need to keep track of account balances. Notice here in our data that blocks don't keep track of account balances. We don't directly know the total value that someone owns. Given what we do know, it's only by looking at the unspent transactions that we can tell who currently owns what. So while we're interested in the ledger, added up by account, we'd need to look through this journal to get that ledger. That is, we'd need to look through the blockchain and its transactions to calculate the current balances for everybody using this blockchain. In practice, there are two main approaches to solving this problem. The thing that allows us to compute the ledger and balances for everyone in Bitcoin and similar blockchains is known as the unspent transaction output set, or the UTXO set. This is an extra database that lives alongside the blockchain. It's what tells us who owns what at the current moment. How? By keeping track of only unspent transactions. And it's maintained by the same computers that form the blockchain network. It always reflects the same information that we see in the transactions of the blockchain. But it's only the UTXO set that turns the data on the blockchain into an actual ledger. This is all a lot of words. So let's put it all together by working through an example. In this simple block, we have 3 transactions. Ripley sends Elizabeth half a Bitcoin, which means if there's been no previous transactions, that Elizabeth now has half a Bitcoin. Now, Andre goes ahead and sends Elizabeth another half Bitcoin. Because she hasn't spent any of the previous Bitcoin, she now has enough to send Jerry 0.9 of a Bitcoin, with the other 0.1 being returned back to her. Now Jerry has 0.9 Bitcoin and Elizabeth has 0.1. That's what we mean by unspent transactions. This running total is what the UTXO set keeps track of. Alright, but how does this look when we add addresses to the mix? Well, it looks very similar. Let's say these are the random anonymous addresses for Ripley and Elizabeth, as well as Jerry and Andre. We've now gone from using names to an actual concept in Bitcoin, which is addresses. The only difference is that in Bitcoin, we don't know that the R1PL3Y address actually belongs to Ripley. We can only see what transactions that address has been involved in. But that's not very interesting. How would this look with multiple addresses involved in a single transaction? The situation is different now because Ripley has sent half a Bitcoin to one address owned by Elizabeth, but then Andre sent half a Bitcoin to a second different address. Now, the UTXO set knows that each of these addresses has half a Bitcoin, but neither address has enough to send Jerry his 0.9 of a Bitcoin. But thanks to Bitcoin's ability to use multiple senders, we can pool together the resources from these two accounts and send Jerry his 0.9 Bitcoin, with the other 0.1 being returned potentially to the first address that Elizabeth has, potentially the second address that she has, or potentially to a third address, maybe one owned by her or her sister. All that matters is that all 1.0 Bitcoin that's being included in this transaction is accounted for. That's exactly what we saw when exploring the Bitcoin blockchain. Every transaction accounted for the entire balance available at an address. Here we had 1.71 Bitcoin, of which 0.04 was sent to this different address, and 1.6 was returned back to the sender. And these icons over here tell us whether that amount was spent or unspent after it arrived at that address. This information is coming from our unspent transaction set. Very cool. Now, rather than using the UTXO set like in Bitcoin, the other main type of blockchain uses a state database. This method is what the popular Ethereum blockchain uses. Just like with the UTXO set, it uses a database that lives alongside every node on the blockchain network. This state database keeps track of the balance owned by every address or account on the Ethereum blockchain. It's a simpler approach and a bit more flexible, but it doesn't provide as much privacy as the Bitcoin model. But overall, it's actually not that different. We still have a special database for balances that lives alongside the transactions. So to summarize, pretty much every company in existence that does accounting has a centralized ledger. Because it lives in one location, it's vulnerable to tampering and things like fraud. It also has a single point of failure. If the centralized database holding that ledger catches fire, the ledger is lost. Hopefully there's backups, but the recovery will probably take some time. In contrast, blockchain forms a distributed ledger, where we don't need to worry about the accuracy of our bookkeepers. It's all logged automatically. We get the advantage of having our ledgers be immutable, which gives us a tamper-proof log of all of this sensitive financial activity. That's exactly what we want in a journal and ledger, giving us this immutable trail or log of transactions that's very useful for financial audits. And our data is stored in a place where no single entity owns or controls it. No one can change what's already written, which gives us some benefits similar to those put in place by common accounting best practices. If you're an accountant, these are things like double entry bookkeeping. This all means that there's fewer chances for things like fraud or other errors. All right, so distributed ledgers have their advantages. But this concept is important for one last thing. Have you ever wondered why the blockchain needs to be a chain? Why not a tree or a graph? These other structures that are very common in the world of computing. Well, for any journal or ledger, we want there to be a single last page, a single most recent state. Imagine if we had a ledger with multiple different correct balances, all living alongside each other. No one would agree on who owns which money. We use a chain, so there's a sequential order to transactions, and the last block contains the most recent ones. That's how we got the blockchain. It all makes sense. All right, I'll see you in the next video. Welcome back. What's the difference between wallets and addresses? And why do I need more than one address? Well, using multiple addresses in Bitcoin is quite common. Say Zoe here has a wallet to store all of her Bitcoin. This one wallet can include several different addresses. Basically, as many addresses as Zoe would want. Each of these addresses might contain only a small portion of her total Bitcoin. If she wanted to pay for something with 16 Bitcoins, well, no one address has enough to pay the entire cost, so she would pool the resources of these first two addresses in a single transaction. We can think of the wallet a bit like a bank account, with the addresses being account numbers with that bank. So a wallet usually belongs to one person or an organization, but it can have multiple valid addresses. The wallet manages all those different addresses and secures them with strong encryption. We'll learn more about the different types of wallets and how they're secured in a later video. All right, but what's the point? Why have more than one address in a wallet? Why shouldn't I just store all of my Bitcoin in one address? We're here at bitcoin.org, an open source community started by the people behind Bitcoin. Now, believe it or not, in order to protect your privacy, the community recommends, let's see here, that we should use new addresses for each transaction, for each new payment, so that it's more difficult to track your transactions and associate them all together. In fact, they go so far as to say that you can even use multiple wallets for different purposes, as an extra step to protect the privacy of your transactions. The only thing is, doesn't this whole idea of protecting your privacy conflict with the whole idea that blockchain is transparent? Aren't privacy and transparency opposites? Transparency on the blockchain means that anyone can see all the transactions that are being made. Anyone can see when they're made, what fees are being paid, and the addresses of everyone involved. It's all public. Remember, this is one of the benefits of blockchain. But transparency and privacy don't have to be mutually exclusive ideas. What I mean is that you can have all the transaction data be public and still make it difficult to track down individual users and their personal information. In the real world, say you're buying a car with Bitcoin. Your Bitcoin address might be anonymous, but as soon as you want to register yourself as the owner of that car, for example, the Bitcoin transaction now becomes associated to your identity. Or consider the scenario where you want to buy some Bitcoin online for cash. Maybe you're buying Bitcoin in return for some American dollars. Well, the bank account that you send the dollars from will be associated with the Bitcoin as soon as you make that purchase. Both the bank and whoever you sent the money to will know your identity. To use Bitcoin for any real-world service, you generally have to reveal your identity and associate it with some Bitcoin address. That address is then traceable to you. And that is why we use multiple addresses. To minimize the amount of transaction history that's available for our addresses and wallets. Because anyone can create as many addresses and wallets as they want, Bitcoin encourages you to take these extra steps to keep your privacy. And other blockchains work in much the same way. You do have to put in a little bit of extra work, but it increases your chances of remaining anonymous. At the end of the day, however, having transactions be traceable might not be a bad thing. After all, tracking down fraud or theft is a pretty good reason to sacrifice privacy. At least you'll probably think so if it's affecting you in the moment. This tug of war between transparency and privacy, and which one is more important, is a huge debate in the world of blockchain. Sometimes a little bit of centralized regulation provides a safety net when bad things happen. For example, when someone steals a credit card, the credit card company will usually flag any fraudulent transactions and pay you back for any losses. With Bitcoin, there's no option for any of that. We'll keep exploring these trade-offs throughout this course. For now, I'll leave you with the question: when is decentralization a bad thing? When is it the best thing? Which side speaks to you more? You can share your perspective on the Zero to Mastery Discord server and see how it compares with others. It's an interesting question, and I don't think there's one answer that applies to all circumstances. The one thing we can do in the face of this uncertainty is to keep educating ourselves. So, let's keep learning. I'll see you in the next video. Welcome back. Let me ask you something. In a world without leaders or rulers, how do we maintain order? That's the question that consensus answers. So what exactly is consensus, and what specific problem does it solve in blockchain? Earlier in the course, we learned that consensus is a way of getting agreement across the blockchain network. When we add a new block, we need a way of getting the latest true state of the blockchain. We need a state that's agreed upon by all the computers on the blockchain network. The challenge with this is that we need to deal with the double spend problem. What's the double spend problem? Say we have 3 coworkers. We have Alice, Bob, and Jerry. They've all agreed to use blockchain for financial transactions. But Alice is not a nice person. She wants to buy Bob's car for some Bitcoin. So she sends a transaction to Bob paying for the car. Bob gives the keys to the car to Alice, seeing that he's been paid. But what he doesn't know is that Alice also sent another transaction, sending that same money to Jerry instead. On the blockchain, depending on the order of when those transactions were received, some nodes would see that Bob here has the money, while some would see that Jerry has the money. So now Bob has lost his car and there's no agreement on who the money belongs to. How do we solve this and reach consensus? How do we maintain one correct order of transactions with a single correct set of data? This is a problem that any sort of payment system needs to solve. However, when we have a centralized payment system, it's easy. We just receive one transaction at a time in order, and if we see that someone tried to spend their money twice, we just reject that second transaction. But when our payment system is distributed, like with the blockchain, it's a more difficult problem. Anyone participating could be an enemy, trying to trick us into adding false data, false transactions that benefit them at our expense. We don't have a central entity, no leader that can decide what is true and what's not. Instead, we need consensus across all the participants. But how? In the next videos, let's look at the 2 main approaches used in blockchain. I'll see you there. Welcome back. Bitcoin came up with a really clever way of reaching consensus using an algorithm called proof of work. The purpose of this algorithm is to have agreement on the true state of the blockchain while keeping it secure. This is not so simple because, as we've seen, control over the blockchain is spread out or distributed. There's no leader or central authority to keep things in check. So, to address this issue, proof of work forces anyone who wants to verify transactions to do a whole lot of hard work. Anyone who wants to participate and add new data needs to prove they've done the work. When a computer participates in proof of work consensus, they add blocks by mining. So block creators are known as miners. When a new block is successfully added, the miner gets rewarded with some newly mined coins. These coins serve as an incentive for people to contribute their computers to do this hard work. Say one of these miners tries to break the rules when adding a new block. They get punished by losing all of the effort that they spent mining that block. Their hard work is for nothing. So what kind of work is it? That's the interesting bit. Remember that blocks have hashes. which we use to ensure that they haven't changed once they're finalized. The problem is, hashes are easy to compute on modern computers. Computers just don't see calculating them as that much work. So proof-of-work blockchains take this idea of hashing, but they make the math problem that you need to solve when creating a block much more difficult. They make it so that you have to generate a specific hash for the data. That is, a hash with a specific target range. Hold on, wait a minute. I thought that the hash was a fingerprint of the data. Once the data has been determined, it should always have one resulting hash, right? That is true. So how do we manipulate the hash to fit in some specific target range? What's the deal with that? Before we keep going, I just want to mention that this video is as mathematical as we'll get in this entire course. So if you're not super familiar with how hashes are calculated, don't worry, just try to follow along with the overall process. We won't get too crazy. Here's how we mine a block in proof of work. To start, the blockchain network agrees on a target hash based on how difficult we want this problem to be. Say our hash is 100000. As a miner, we want to come up with a valid hash for the data in our block that's below this target hash. For example, 0.90000. The smaller the hash, the harder the problem, because the range of correct hashes is narrower. In this case, we're rejecting any hash that starts with a 2, a 3, a 4, and so on. Now, we've agreed that the way hashes work, given a set of data, only one possible hash can ever be generated by that data. That's how hashes are used to detect changes. It's one of their main features. So looking at the blockchain, miners shouldn't be allowed to change any of our transactions. So how do miners make sure that they can generate a hash in this target range? What data can they manipulate to change that hash? They add something called a nonce to the data. This is an arbitrary number that's used only to change the hash. It doesn't change the transactions or the meaning of the block in any way. It lives inside the block, but it's only used to change the hash. So as a miner, we do a bunch of calculations as fast as we can, trying different possible values for this nonce so that our hash is less than the target. So we try one nonce, calculate the hash as fast as we can using the block's data, and we come up with a guess. But it's too large. So we need to keep working. We pick another nonce value, do our calculations all over again until we succeed. We've found a hash that's less than the target, which means we've won. We get that block award of freshly mined coins. Once this valid hash is found, it's broadcast to the entire network. And this block is added to the blockchain. Anyone on the network can easily verify that the guess is correct because they're now aware of the correct nonce. It's part of the block. This all works because the miner has to guess a very large amount of values before they're successful. So it's not easy for someone to just come along out of the blue and add their own data to the blockchain. So to summarize, Hashes are easy to compute. For example, Bitcoin uses a SHA-256 hash, which is a common hash that any typical computer can compute in much less than a second. Other blockchains might use different hashes, but in general, hash functions aren't designed to take minutes, hours, or years to compute, which is what we want for the blockchain. But thousands and thousands of hashes are much more difficult. They take longer even for very powerful computers. The difficulty of our proof-of-work problem can be adjusted as computers become more powerful, just by making this target range smaller. Making the range narrower means that there's a smaller set of possible hashes that are correct solutions. One way of looking at proof of work is as a lottery where you're guessing the correct winning number. The way this lottery is designed, there's many correct guesses. But if we find the lottery is too easy and people are winning too often, we can make the lottery more difficult. We'd do this just by decreasing the amount of correct numbers, the numbers that win the lottery. Another way of looking at it is that with proof of work, transactions are protected by a computational race, which faces any attacker off against the entire rest of the network. The way this works out, because everyone is competing for the correct solution to this proof of work problem, for that correct nonce, you would need control over half the computing power in the network to have just a 50% chance of solving a block before someone else. And you'd need a much higher amount of computing power to compute several blocks in a row faster than the rest of the network. This is why blockchains like Bitcoin generally wait several blocks before considering received money final. Because blocks build on each other, transactions further back in the blockchain are more secure. To carry out a double spend attack on a transaction 4 blocks old, an attacker would have to win that race for a solution ahead of the rest of the network for 4 blocks in a row. Not very likely. Blockchains tend to be only vulnerable to double spend attacks near the end of the chain, which is why it's recommended to wait several blocks before considering received money final. You can adjust this based on your needs. For transactions worth less money, you can wait 1 block, or in other words, wait for 1 confirmation, whereas for larger transactions, you might want to wait up to 6 blocks or more. 6 isn't a magic number. It's just an amount chosen by a popular Bitcoin application. But it does give you a reasonable amount of confidence that the transaction is valid. The challenge for real-world use is that waiting for 6 blocks, if each block takes, say, 10 minutes to confirm, would mean you're waiting around for an hour before your transaction can be confirmed. But this is how we secure the blockchain with proof of work. The power of this approach is that nothing requires trust. Anyone on the network can be malicious, and the power of the network as a whole makes the whole system secure. The computations are so hard that no one person could compute them on their own. The work we do for a correct guess is proof that the entire network is working together. On average, it might take a typical computer a few years to solve a single block, whereas it takes the network just a couple of minutes. Very cool stuff. All right, I'll see you in the next video. Welcome back. Proof of work is very effective at securing the blockchain, but it consumes a huge amount of energy. Exactly how much? Prepare to have your mind blown. We've covered how proof of work works. We do massive amounts of inefficient computations, guessing the hash until we find one in the target range. We do this to ensure that no one adds false data, to make sure that transactions don't suffer from the double spend problem. And it works. But at what cost? The University of Cambridge tracks what it calls the Bitcoin Electricity Consumption Index, where it calculates the total usage of electricity for the Bitcoin network. We can see that the live estimate as of the recording of this video is about 15 gigawatts of power demand and 130 terawatt hours of electrical consumption over the course of a year. The power demand is the rate at which power is being drawn by the network. That is, how much power does it need at any one moment? And electrical consumption is the total amount of electricity used over the course of a year. But unless you're an electrical engineer, maybe this doesn't mean too much to you. The cool thing about this site is that they make these numbers more accessible by, for example, showing this graph of Bitcoin power demand over time. What does this tell us? Well, the amount of power needed by the Bitcoin network is actually going up and down. But on average, it's definitely going up. We can see this even better by looking at another graph of the overall electricity consumption. This is very clearly going up. Okay, but what do these numbers actually compare to in the real world? My favorite part of this page by University of Cambridge is the comparisons. Let's take a look. If we scroll down to the total world production and consumption part here, this is crazy. Bitcoin is using, wait for it, not too far from 1% of all the electricity produced in the entire world. Whoa! My mind was just blown again. Sorry about that. In some areas, Bitcoin mining facilities tap directly into the world's energy at the point of production, instead of accessing it through the power grid like your average home or office building. Scrolling a bit further down, we can see that Bitcoin consumes about as much electricity as all gold mining activity. Interesting, because as we'll learn later, Bitcoin is often compared to gold, sometimes being called digital gold. And if we go down to the next part here, we can see how Bitcoin compares to other common activities that use electricity. For example, air conditioning around the world. How much energy goes into copper production, or all the data centers around the globe. This one is crazy too. Think of all the data stored on the internet, or all the data being sent back and forth over various networks. Bitcoin is not too far off from using the same amount of energy. And it uses more than all the TVs and lighting in the United States combined. Remember, we're talking only about Bitcoin here and not about any of the other blockchain networks that are out there. If we scroll all the way down, another interesting statistic is a comparison between countries. Based on country data from 2019, we can see Bitcoin consumes about as much electricity as countries like Ukraine, Egypt, and Poland. If you're interested in seeing these numbers for yourself, I'll attach a link to this page to the video. So, is all of this worth it? That's quite the question. It's definitely very wasteful. All of this waste and the corresponding negative effects on the environment are one of the largest current criticisms of blockchain. But how is the effect so large? Just for the blockchain? Are we really using that much energy? Looking specifically at Bitcoin as an example, more and more money is being transferred on the Bitcoin network. So to secure it, the proof of work problem has been made extremely difficult. In practice, these target hashes are very, very small. Instead of limiting the hash to maybe 5 to 10% of possible guesses, with Bitcoin, it needs to be much smaller, with fewer acceptable options. In Bitcoin, for every accepted hash, there will be billions and billions of rejected hashes. The work we have to do for mining is really hard, even for the absolute best computer CPUs. So, to solve things faster, we've created all this specialized hardware. Originally, graphics cards and chips called FPGAs, miners are now taking advantage of computer chips specifically designed for mining Bitcoin. They use what's called application-specific integrated circuits, or ASICs, which are much faster than our computer's CPU or even graphics cards at doing many repetitive calculations in parallel. In practice, it looks like this, with massive warehouses full of this powerful hardware. No laptop stands a chance. With all of this specialized hardware, we can do much more work in a shorter period of time. We get more Bitcoin as a reward. But the proof of work problem keeps getting even harder. The cycle continues, and we need even more power to solve our proof of work problem. So, is the solution to ban proof of work blockchains? Well, maybe, if we had a better alternative. But surprisingly, one study from early 2022 found that after China made moves to ban Bitcoin mining, the carbon footprint of Bitcoin actually jumped 17%. What that means is more pollutants like carbon dioxide were being produced as a result of all the energy being wasted on Bitcoin mining. The ban actually forced miners to use less environmentally friendly approaches. And let's be clear, this energy consumption is wasteful because it's useless. The hard work being done serves no purpose beyond just validating consensus. It's like solving a problem that you created for yourself. At the end of the day, you're still back to square one, back to where you started. Only you've spent a whole bunch of energy to get there. Hopefully, in situations like this, we learn something from the experience. We learn a better approach, and we improve. And luckily, that's what's happening in the world of blockchain. We'll find out one way that we can improve in the next video. I'll see you there. Welcome back. In response to criticisms about the wastefulness of proof of work, another approach to reaching consensus is taking off. It's called proof of stake, and it makes blockchain a lot more compelling to its main critics. So, how does it work? Let's recap for a second. In proof of work, you race against other validators or miners to get the privilege of adding a shiny new block to the chain. Now, in proof of stake, you instead set aside some coins and get randomly selected as a validator based on how many coins you've set aside. It's a lottery system, and those coins are called your stake. If you try to add an invalid block, you'll be punished by losing that stake. But if you play by the rules, you'll get awarded with some brand new coins. With this approach, we're much less wasteful. There's no need for massive warehouses full of specialized hardware because the competition isn't about quickly solving a problem, but rather how many coins you're willing to set aside as your stake, as collateral. The blockchain is secure because those who approve transactions that turn out to be fraudulent will lose the coins that they've staked. The idea is that by misbehaving, any attacker risks more than they're able to gain. So they behave honestly out of selfishness. Generally, multiple validators will go through each block to double check, but the bulk of the reward goes to just one person, the person chosen in the lottery, where those who stake more coins get more tickets, more chances of winning that lottery. Now, in proof of stake, the people who add blocks are called validators, as opposed to miners. Although the term mining is sometimes used as a general term for both proof of work and proof of stake. So it's best not to get too caught up in the terminology. These proof of stake blockchains exist today. Some of the early proof of stake blockchains include Cardano, Polkadot, and Solana. While on the other hand, there's other blockchains like Ethereum that have decided to transition from proof of work to the more energy-friendly proof of stake. This kind of transition is not an immediate event. It takes considerable planning. But ultimately, the people behind Ethereum have decided that the benefit compared to proof of work is too significant to ignore. Not only is proof of stake more environmentally friendly, but you can also earn interest on the coins that you already own. All you need to do is stake some coins for your chance to get a reward. It's just like investing in a company on the stock market. When you stake some coins in a blockchain, you're supporting that blockchain with your money, with your coins. Another benefit is that you don't need any special equipment for staking. There's no need to build these massive warehouses of powerful computers like you would with a proof-of-work blockchain. What this means is that more people can participate in validation. And the more people participate in validation, the more decentralized the blockchain. Every user with some stake is now helping to maintain the security of the blockchain. It's a win-win. So in that case, is proof of stake entirely better than proof of work? The truth is, no one actually knows. At least, not when it comes to security. Proof of work has already proven itself to be able to secure billions of dollars worth of bitcoins for well over a decade. It hasn't been without flaws, but for the most part, it works really well at preventing fraudulent transactions. Proof of stake, on the other hand, is much younger, and while it's based on some very promising ideas, it hasn't proven itself quite as much. Most likely, which one is better or which one is more secure will depend on how you look at it and what your goals are. These are open questions in the field of distributed computing. There might not be one correct answer. In fact, blockchain is basically one giant experiment where these questions are being tested under the most hostile possible conditions, where every hacker on the planet would like a piece of all the money that's being stored on the blockchain. In the end, history will be the judge of whether this experiment was a success or a failure. All right, in the next video, let's solidify our understanding. We'll walk through proof of stake step by step. We'll learn a lot, so I'll see you there. Welcome back. Let's walk through the proof of stake process step by step to make sure that we're not overlooking anything. This should be fun. Say we're really excited about the blockchain and we've finally bought some coins. Now, we want to take things a step further and become a validator. To support the blockchain and get those shiny rewards that we know validators get. Who doesn't like getting paid for their work supporting something that they like, right? So, we take some of our coins and we lock them away in a box at an address that we can't access. These coins are our stake. They show that we're invested in the well-being of this blockchain. With proof of stake, usually there's a minimum amount of coins that you need to stake before you can become a validator. For example, 32 coins, which might be a lot if a single coin is worth thousands of dollars. If we can stake enough coins, we're added to the list of validators. This is important. For the blockchain to remain secure, it needs some way to prevent bad actors, malicious users, from taking over the validation of new data. Proof of stake accomplishes this by requiring validators to have a significant amount of coins locked away. Any attacker hoping to take over 51% of the network would need to buy 51% of all the staked coins in order to mount an attack. And if they don't succeed, they'll lose their entire stake, which at that point would be huge. So we've staked some coins, and now we're waiting patiently for our chance to be the next validator. So how is this determined? Who gets to do the next validation? Who gets the reward? In proof of work, the person who wins the race to find the hash gets selected as the validator. But in proof of stake, it's more of a lottery system. The chance of being selected is based on the amount of coins that you own that you've put towards staking. Now, there's different flavors of proof of stake. In some of them, it's just the amount of coins that directly represents your chance of getting picked in the lottery. In some, it depends on how long you've held those coins. And in others, it might be that anyone who's staked anything gets an equal chance of being a validator. The point is, as a validator, you're selected via an automatic selection process. This process is public, so anyone can see how the process works and that it's fair. However, the result of the selection process should ideally be kept secret, so only the person who's been selected knows that they've been selected. Why? Well, they might be tempted or corrupted by another party to add fake data to that block, to validate an invalid block. Now, once they add that block to the chain, they can then provide proof that they were selected. This process must also be fair. We want validators to be selected based on the stake they own. But we might also want to balance things to make sure that the very rich aren't selected too often, so they don't control a disproportionate amount of validation power in that blockchain. Okay, some time passes, we've waited around long enough, and we're finally selected in the lottery. We're now taking charge. We go through the transactions in the block, and if they look accurate, we validate that block. It's now our chance to collect our reward. In proof-of-stake blockchains, the reward tends to be mostly the transaction fees from the block that we just validated. There's less hard work being done, so the block itself doesn't need to create as many new coins. We don't need to introduce as many resources into the economy. Of course, the exact details of this will depend on the blockchain. And that's it. If we ever decide we no longer want to participate, we can take our stake back and we're removed from the list of validators. But by now, hopefully, we've earned some coins and we've done our part to maintain the security and efficiency of the blockchain. I'll see you in the next one. Ethereum is the world's first programmable blockchain. What does that mean? Well, the Bitcoin blockchain is great for financial transactions. But what else can we do with the blockchain? In 2013, a developer called Vitalik Buterin came along and said, digital currencies are nice and all, but we can use this idea of the blockchain for so much more. His vision? To create an unstoppable, self-sustaining, decentralized world computer, transparent to everyone and free from issues like censorship. Whoa. Vitalik went on to create the Ethereum blockchain, which launched in 2015. Ethereum follows some of the same basic ideas of the blockchain that we've been discussing so far. It keeps track of millions of transactions that are grouped into blocks. Each block is linked together to the previous block by a hash. Just like in Bitcoin, Ethereum has its own currency called Ether. But the transactions in the Ethereum blockchain are completely separate from Bitcoin. Ethereum expands on the ideas of Bitcoin's blockchain. It stores more data and has the power to run games and applications. So how exactly does any of this work? Let's find out how Ethereum improved upon Bitcoin and how the Ethereum blockchain is structured. Inside of the data for each block, instead of just storing the list of transactions, Ethereum stores 3 collections of data. Every block has a state, a collection of transactions, and a collection of receipts. Why break things down like this into 3 parts? It'll make sense if we know what each of these collections is responsible for. Let's start with the global state. This is what stores all the Ethereum accounts. It contains a map of each account on the Ethereum network. Each account has a 20-byte long address. The state maps all these addresses to the account available at that address. So it stores these key value pairs where the key is the address of the account and the value is the account object itself. So what's in an account? There's three main things. We have the account balance, or how much Ether is owned by this account at this address. And this account balance completely replaces Bitcoin's unspent transaction set. Thanks to splitting things up this way, we get a much simpler way of looking up how much Ether is available for an account. And here's where it gets interesting. An account can have some code, a program that gets executed when this address gets a message to execute that code. The message comes in the form of a transaction being sent to the account. It works a bit like a vending machine or a jukebox. You know where you put a coin into the machine and it starts playing some music? The code in our account responds to a transaction in much the same way, by running the code. And because it lives on the blockchain, this code is immutable. It can't be changed after it's set. But this ability to run code is what made Ethereum so revolutionary. This feature allows blockchain to be used not just for finance, but also for an infinite amount of possible applications. In Ethereum, a computer program saved to an account like this is called a smart contract, and it's something we'll be talking about a lot throughout the rest of the course. But to help the code do what it does, we also have some storage. This is where all the data for the program lives. It's empty when the account is created, but it can be used to store whatever the program or the smart contract needs. It can be modified by the code, and it sticks around until it's deleted. So that's what an Ethereum account is: a balance and optionally some code and storage. All right, so that covers the global state, but what about the transactions? This is Ethereum's equivalent of the transactions that we stored with Bitcoin. It keeps track of all the transactions that have been requested between two accounts. It tells us exactly how much Ether is being sent, who is that Ether being sent to, and how much of this gas fee will be paid as a result. Wait, gas what? Gas is a fee required to successfully complete any transaction on the Ethereum blockchain. This gas fee can be different depending on what the transaction is doing. For example, are we reading from some account storage, or are we moving Ether between two accounts? And it's paid as a reward to the computer validating that transaction, to the computer adding that block to the blockchain, the mining computer. This gas is a way of paying for the energy needed to power that transaction. It's an incentive for people to participate in the blockchain, to put their computers to work so that we have more copies of the blockchain and more computers willing to validate new transactions. Remember, this is a big responsibility. So Ethereum includes gas in the reward for adding a new block. This is in addition to the reward paid for mining or validating that block. Both are included. An interesting side effect is that as Ethereum gets more popular with more transactions, these gas fees get more and more expensive. Alright, that's transactions and gas. Finally, we have the receipts collection. Just like you get a receipt from the store when you buy something, Ethereum transactions generate receipts. These receipts let us know what the outcome of each transaction was. Did it succeed? Was it canceled? What happened? And there you have it, the structure of the main collections tracked by the Ethereum blockchain. Which is fine and all, but how does Ethereum run the code that's stored under an account? How do we go from some code stored on the blockchain to that unstoppable distributed computer that Vitalik envisioned? That is a very good question. We're getting to the fun stuff, so let's keep it going. I'll see you in the next video. Welcome back. How does code run on the Ethereum blockchain? What really is a smart contract? And how does it work? Let's dive in. Remember the global state? Just in case you've forgotten, this is where we map accounts to addresses. All accounts have the ability to receive, hold, and send Ether. That's what the account balance tracks. But beyond that, accounts are divided into two different types, each with their own special purpose and capabilities. We have externally owned accounts and we have contract accounts. Let's break this down. Starting from externally owned accounts, these contain only an account balance, the balance of coins of Ether that's available at this account. These accounts are controlled by external actors, people, human beings like you and I who live outside the blockchain. On the other hand, contract accounts, in addition to that account balance, also contain some code and some storage. The code is in a computer language known as Ethereum bytecode. This bytecode is what the computers on the Ethereum network know how to execute. That's how the blockchain runs code. The account storage acts as a persistent memory for that code, so it doesn't forget. Now, unlike externally owned accounts, contract accounts are not controlled by people. Instead, they act automatically. They're controlled by their own code. For this reason, contract accounts are very often called smart contracts. Whenever someone is talking about a smart contract, at least in Ethereum, they mean one of these contract accounts. So, to avoid confusion, going forward, we'll be calling any account with some code a smart contract. There's two main ways that we can interact with smart contracts. We can create them and we can send messages to them. Let's look at an example. Imagine you own 100 Ether. You are an external actor. You have an externally owned account. With this account, you can create a smart contract just by making a transaction on the blockchain. Once that contract has been created, it can be triggered by a different type of transaction, a message call. Both message calls and contract creation are transactions in the blockchain. They update the Ethereum global state, which contains all of our accounts, whether they're contracts or not. When you create a contract, you make a transaction that saves the contents of that contract, the code, in the Ethereum global state under a new account. Once it's been saved, you can now make message calls to the address where that contract was saved. How do message calls work? Well, when an account with some code receives a message, it starts running that code. In other words, the smart contract starts executing. It'll load any data from storage, run through its code, and update the blockchain accordingly. So it's these message calls that trigger the contract's code to actually run. They're how we control when the contract's code runs. So that's for externally owned accounts, but what about contract accounts and the smart contracts they contain? These are very much the same. They can make their own message calls, sending messages to either externally owned accounts or even to other smart contracts. In fact, they can even create new smart contracts, like their own little smart contract children. It gives them a lot of power, and it means that they can get pretty complex. They can execute a long list of different actions, transferring Ether between accounts, doing computations, accessing storage, and, of course, even creating new data, new accounts, new messages. The possibilities are endless. But all this power introduces a problem. What happens if someone malicious, someone evil like Alice, comes along and creates a smart contract that runs forever? This evil contract would waste the resources of the entire Ethereum network, causing a denial of service attack, where no other contracts can execute. She could take down the entire Ethereum network. Luckily, the solution to this is built in to how Ethereum works. Remember gas? Every operation that a smart contract can do has some predetermined cost associated with it. And the account messaging that contract has a limited balance of Ether. It needs to pay up to execute any computations or transactions. If we run out of our Ether and we can't pay the gas, the contract won't get executed. We won't be able to create new contracts or make message calls to existing contracts. So gas is not just an extra reward to pay validators. It's also a protection mechanism to prevent people from creating contracts that execute forever. All right, to summarize, we have externally owned accounts with just account balances, and we have contract accounts, which are our smart contracts. Any account can interact with another account by sending a transaction. With contracts, we can create a new contract, or we can message an existing contract to run its code. There we have it. Let's continue in the next video. I'll see you there. Welcome back. Here we go. The final piece of the Ethereum puzzle. The Ethereum virtual machine. This is what allows computers on the Ethereum network to run code. It allows them to execute Ethereum bytecode, the computer language that smart contracts use. With the Ethereum virtual machine, we use the network of computers that validate new blocks as a sort of distributed computer to run programs stored on the blockchain in addition to validating transactions and blocks. To understand how this Ethereum virtual machine works, we need to break down our idea of what one computer on the Ethereum network looks like. Of course, the basic requirement is that we need the physical computer, the computer hardware that lives in some room or some warehouse that physically does all the work. But we now have all this Ethereum software that runs on that computer. We can break this down into a few different layers. On top of the physical hardware, we have a piece of software called the Ethereum client, which turns our general purpose computer here into an Ethereum node, into something that understands the Ethereum protocol. As a node, this machine can communicate with all the other Ethereum nodes on the blockchain network. It can keep track of the state of the blockchain. It can verify the transactions in a block. It can do its part in making sure that the data is accurate and the blockchain is secure. There are many of these Ethereum clients available, but one of the most popular is Go Ethereum. This is the official client. It's completely open source, and you can browse its code on GitHub over here. If you're interested, you can even turn your computer into an Ethereum node just by running this software. Part of this software is what's known as the Ethereum Virtual Machine, or just EVM. This is a virtual computer maintained by thousands of connected nodes, each running a valid Ethereum client. Running a node also means we're running an Ethereum virtual machine. And this virtual machine is what allows us to run the code that's included in a smart contract, because it understands how to run Ethereum bytecode. In fact, Ethereum bytecode is also known as just EVM code. If we think of the data on the blockchain as the state of the machine, as its memory, the Ethereum virtual machine is then what transitions the blockchain from one state to another. Given some input and a smart contract, it computes the next state of the blockchain and saves it to the next block. All of this happens automatically. Ethereum is what's known as a Turing-complete blockchain, because using just this approach, the EVM can be used for any possible computation, anything you could ever imagine. That's what Turing-complete means. So just about any application could be moved to the blockchain. But that doesn't necessarily mean that blockchain is the right tool for the job. Have you ever heard the phrase, if the only tool you have is a hammer, you tend to see every problem as a nail? The same could apply to blockchain. We want to make sure we're using it only for the applications where it makes sense. Okay, to really sum things up, we could say that Ethereum is basically just the accounts and transactions stored on the blockchain, plus the Ethereum virtual machine, with some added mechanics like gas included to make things run a little bit smoother. There you go. Now you should have a solid foundation on the internals of Ethereum, the blockchain that took what Bitcoin did and raised it to the next level. All right, I'll see you in the next video. Bye for now. Here we go. So far, we've been discussing a lot about blockchain and Bitcoin. In this video, we'll start our discussion on blockchain applications by taking a closer look at a very interesting concept: cryptocurrency. What is it? Cryptocurrency is a kind of digital currency designed to work globally around the world. So what makes cryptocurrencies different than the currencies we already know? Traditional currencies like dollars, euros, or yen rely on some central authority like a government or bank to regulate them. For the US dollar, this central authority is the Federal Reserve. That's the central bank of the United States. The Federal Reserve maintains the total available supply of US dollars, regardless of whether they're being bought and spent in the United States or Canada or anywhere across the world. If we want to send and receive our dollars digitally, we need to use a third party, a middleman, some service like PayPal or an online bank, which would decide based on their internal rules if our transaction was allowed, and of course, they would take a small cut for the service that they provide, for moving our money from one account to another. As users, we're not too happy about these extra fees. We'd like to avoid them where possible. Now, unlike traditional currencies, cryptocurrencies don't rely on a central authority. The rules of a cryptocurrency are followed automatically based on the code and transaction rules of the blockchain. Because these rules are distributed across the entire blockchain network, there's no single point of failure. And we don't need middlemen like PayPal in order to send our money to an old friend, to a business that we support, or even to a family member across the ocean. Just like normal money, we can use the coins or tokens of a cryptocurrency to purchase real-world goods, like cars and tickets to sports events. They can be used as investments to save up for a home or retirement. Or they can be used entirely in the context of the blockchain. For example, to encourage others to join the blockchain network or to enable transactions. Now, Bitcoin, or BTC, is one example of a cryptocurrency, but it's far from the only one. Since the introduction of Bitcoin, there's been some major cryptocurrencies, including what we call Ether, or ETH, which is the currency of the Ethereum blockchain. You also might have heard of Dogecoin. Originally a copy of Bitcoin created as a joke, it's now one of the larger cryptocurrencies. So what am I getting at here? Just like we have dollars, euros, yen, and other currencies in the real world, there's thousands of cryptocurrencies nowadays as well. On this website, coinmarketcap.com, we can see a list sorted in order from the most valuable to the least valuable. Now, to measure the value of a cryptocurrency, we use what's called the market cap. This is the price of one coin multiplied by the total amount of available coins. It changes over time, but as of the recording of this video, for example, we have Bitcoin having a market cap of over $1 trillion. That's higher than the GDP, or gross domestic product, of most countries. It's equal to the total amount of all the goods and services in countries like Mexico, Indonesia, and the Netherlands. This absolutely blows my mind. And it shows that whether we like it or not, blockchain has already changed the world. Now, each cryptocurrency has its own price, which is how much one coin or token of that currency is worth. Looking at Ethereum, we can say that if we own some Ether, we want the price of Ether to be high because then yours will be worth more. You'll be able to trade your Ether for more things that you find valuable. Each of these cryptocurrencies has differences in how it's best used, in fees, how many transactions can be processed, and of course, the most important thing is the value of each currency. If you study the movements of the prices in all these cryptocurrencies, you'll realize that most of them are very closely tied to the price of Bitcoin. What I mean is if the price of Bitcoin goes up, say, 4%, the price of many of these other cryptocurrencies will go up somewhere around 4% as well. Now, some of these other cryptocurrencies do have their own unique uses and strengths, like Ethereum, with its ability to run code on the blockchain, or Tether, which is designed specifically to follow the movements in price of the US dollar. But beware, there are many coins that are mostly just cheaper copies of Bitcoin with just a few changes. Not all of them are reliable or trustworthy. The big ones that have the highest market cap that you see here are generally the ones that are most proven. They've been around for the longest time, have the most users, and have probably been tested by hackers interested in getting access to all this money. But as with most investments, even with the reliable ones, it's important to remember that it's possible you'll lose everything you put in. Oh, and by the way, before we go, when you hear somebody talking about crypto, usually they mean cryptocurrencies. But it's also possible they're talking about blockchain as a whole. Or it's also possible they're talking about cryptography, which is the set of technologies and algorithms that programmers use to keep our data secure. To avoid confusion, you want to be explicit about exactly which form of crypto you're talking about. All right, let's keep learning. I'll see you in the next video. Welcome back. We've seen there's hundreds and hundreds of different cryptocurrencies. But what makes them different from each other? Let's break things down into a few different types of cryptocurrency. First off, if you were paying attention, you'll remember that I mentioned cryptocurrencies can use coins or tokens. This is probably the most common distinction you'll come across. Coins, like Bitcoin, are a reward for mining, for processing transactions on the blockchain network. They're native to the blockchain. They're built in to how it works. But new blockchains like Ethereum or Bitcoin are pretty hard to make and to maintain. So, in many cases, cryptocurrencies will reuse existing blockchains. These are known as tokens rather than coins, because there's already a native coin on that blockchain. For example, we have Ethereum with its coin Ether, but there are tokens that make use of Ethereum as well. There's a lot of these, but for example, we have Tether and USD coin, which are both designed to mirror the price of the American dollar. And there's others like Uniswap, Shiba Inu, and Chainlink. We can also break down cryptocurrencies based on whether they're useful as a store of value or as a transactional currency. For example, Bitcoin was originally created to be similar to gold, which has a long history of being used as a store of value. When you buy something to store value, You're betting that it will maintain its value over time, as opposed to depreciating. Gold is seen as a store of value because it's been valuable for thousands of years. It can be moved around, and it can sit on your shelf for years and years without breaking down. A car, on the other hand, is a very poor store of value. Cars depreciate quickly because they break down and new, better models are created. Cryptocurrencies like Bitcoin are a bit different, but there is a limited possible supply, just like with gold, and very few Bitcoins are created each day. In fact, it's becoming more and more difficult and expensive to mine Bitcoins. The way they were designed is that the remaining amount of Bitcoin is cut in half about every 4 years. This is called the halving, and it means that miners get less and less Bitcoin over time. So the reason Bitcoin is good as a store of value follows from a basic idea in economics. Because there's a finite, limited total supply of Bitcoin, as the demand for them increases, the price will also increase, which means they maintain their value. All right, what about transactional currencies? Some examples of these include Ripple, also known as XRP, and Stellar, also known as XLM. These have much lower transaction costs and much faster transaction processing times. Lower transaction costs means that it makes more sense to use transactional cryptocurrencies for small purchases. Imagine buying a cup of coffee for $5 and having to pay $20 of transaction fees. Or imagine having to wait 20 minutes while that transaction is processed. While the actual transaction fees and processing times vary, that's basically the situation we have with Bitcoin. And that's what transactional cryptocurrencies are designed to avoid. They're more usable in our day-to-day lives. Finally, we have mineable versus non-mineable. Let's start with mineable. These are the cryptocurrencies where you can claim ownership of some amount of new coins just by contributing to a node, by contributing to the creation of new blocks in that blockchain. We've seen that this is how Bitcoin encourages people to do all the hard work of maintaining copies of the blockchain and the hard work of validating new blocks. However, being mineable isn't the only option. What's the alternative? The creator of a non-mineable cryptocurrency generally owns all the coins or tokens right from the beginning. They then decide how these coins or tokens are distributed. In most cases, all of the possible coins that will ever exist are distributed in what's called the initial coin offering, or ICO. When the creators announce their ICO, people can trade other cryptocurrencies for a portion of those initial coins. One example of such a non-mineable cryptocurrency is Ripple. Ripple is both a company and a blockchain with its own non-mineable coin. Ripple is a very interesting company, and I'll attach some links to read more about it to this video. However, it's worth noting that Ripple collaborates with hundreds of financial institutions around the world. They've taken investments from many other companies, including Accenture, Google, and Andreessen Horowitz. Naturally, This kind of thing makes these non-mineable cryptocurrencies less decentralized. The owner or group of owners has control over the total supply, just like with a central bank. But as we saw earlier, Ripple also has lower transaction costs. So the centralization comes with some benefits. Interesting, right? And there you have it. Next time someone mentions a cryptocurrency that you don't know, ask, is it a coin or a token? Is it useful as a store of value or is it more transactional? And is it mineable? That will get you off to a really good start. You could divide cryptocurrencies into many more categories, but these are the ones that I feel will give you the best starting point. Instead of looking at things that can change over time, it's more efficient to look at how cryptocurrencies actually behave based on their fundamental features, based on how they were originally implemented. All right, good stuff. I'll see you in the next video. Welcome back. Who needs cryptocurrencies? What good do they do? We know that they don't rely on a central bank or any single authority to control the total available supply. Take the United States. By controlling the supply of how many dollars are in circulation, the Federal Reserve has the ability to indirectly control the value of the dollar. Cryptocurrencies, on the other hand, live on the blockchain, so they're decentralized. For some people, this could mean the difference between poverty and financial freedom. Why? Currencies are inflationary. You can have $100 now, which might be able to buy you a fancy new road bicycle with all the bells and whistles. But now, 5 years later, we can still have the same cash. It's still $100, but it's now worth only a really basic used bicycle. That's inflation. One of the reasons this happens is that governments have the ability to print more money, which means that any existing money that's in circulation, that's actually in your hands or in your bank account, will be worth less because there's now more total money available. Governments are able to manipulate the currency depending on their needs. Maybe it's because they need more money to avoid a financial crisis. Or maybe they just want to encourage people to spend the money that they already have right now, as opposed to in 5 years. This isn't always a bad thing. If you're a store owner and you rely on people buying your products, a little bit of inflation can encourage customers to spend their money, as opposed to holding on to it indefinitely. This can help keep your store alive. But in some countries, money is hyperinflationary, which means that it loses value a lot quicker. It could be because the central authority managing the country's currency is corrupt. Or maybe they're just not able to maintain the value of that currency to buy things relative to other currencies. Whatever the reason, the government effectively has editing privileges in the database that we call money. They can add to the money supply whenever they so choose. For those who don't find inflation appealing, or who would rather not have their government involved, cryptocurrencies might sound amazing. No government has editing privileges, because the currency lives on the blockchain, which is immutable. So there's no chance the government will create inflation by adding to the money supply. In fact, some cryptocurrencies are designed to be deflationary, with the total supply decreasing over time. So the coins you own now get more valuable over time. In theory, this would make a deflationary currency a very good investment. However, you do have to keep in mind, even with deflationary currencies, any value that a coin has is determined by whether someone is willing to trade you for that coin. If there's no demand from others, your coin still won't be worth anything. No amount of inflation or deflation will change that. To summarize, cryptocurrencies provide a global currency that we can send and receive without relying on centralized governments or middlemen like PayPal. If the alternative is hyperinflation, this sounds great. It's also useful for families in countries like India, Venezuela, and the Philippines who rely on remittances. These are international money transfers from higher-earning members of the family. These family members usually live overseas in countries where higher earnings are more common. But they need to pay very high fees for these remittances because of international regulations and transfer fees. Fees which are potentially much lower with the use of cryptocurrency. Now, over time, the big question of how and when to regulate cryptocurrencies is growing more and more. There's new developments almost every week, and every government is taking different approaches. Some of the more extreme examples include El Salvador. In late 2021, they started an experiment where Bitcoin was made legal tender alongside the US dollar, while in China, the government has made moves to ban all cryptocurrency-related activities. So where will all of this take us? We'll just have to wait and see how cryptocurrencies will be treated in the long term across the globe. But their appeal is strong for those who can't otherwise rely on a stable currency or stable banks. That's all for now, and I'll see you in the next one. Welcome back. What are the problems with cryptocurrency? What mistakes do people always make when getting into it? And how do I prevent myself from losing all my money? These are the questions that we'll explore in this video. There are many criticisms of cryptocurrencies. Some focus on the technical details, while others focus on the long-term effects cryptocurrencies will have on the world. For much of this course, we focus on the technical side of blockchain. But this video will discuss the most direct criticism of cryptocurrencies. Things that can't really be changed with just some technical upgrades. We've learned that cryptocurrencies are the biggest application of the blockchain. They aim to move power away from centralized banks and governments. And there are thousands of them. But how are they really used? In the earlier days of Bitcoin, between 2011 and 2014, By far, the largest store that made use of Bitcoins was a black market, used to buy illegal goods and services. It was used for some horrible things, and while it was eventually shut down, it still leaves a bad mark on the world of cryptocurrency to this day. This is a big deal because the Bitcoins that were transferred on this market would today be worth many billions of dollars. So when you buy some Bitcoin and its value goes up, consider who exactly is profiting as a result. Who's gaining the most? It might be you, it might be an early adopter of Bitcoin, or it might be a criminal. Even now, cryptocurrencies are still getting a bad name because they're popular with scammers and hackers. One of the most common attacks on organizations to this day is ransomware. This is where hackers encrypt your data and ask for some payment before you can get back access to it. And it's cryptocurrencies that are used to pay these criminals because of their added anonymity, the ease of sending money internationally, and the lack of regulation around those payments. This has gone far enough that cryptocurrency and ransomware are often linked together. The rise of cryptocurrencies has sped up the pace at which these ransomware attacks are made. There's now this added incentive because of the increased likelihood that the criminals will get paid for their crimes. Nowadays, there are still very few stores that accept Bitcoin and other cryptocurrencies. While there have been some cases where you can use cryptocurrency to buy tickets to a concert or to buy a car, these uses are still very limited. Which makes sense. Most cryptocurrency doesn't actually make a good currency. Why not? What does that even mean? Let's look at some examples. Say we own a local coffee shop. How much do we charge for a coffee? Normally, we could look at how much a coffee costs us to make and look at the price of competing coffee shops and set our own price based on that. But with cryptocurrencies, even with reasonable transaction fees and quick processing times, they tend to be too unstable for practical use. How can we price our coffee when the value of our currency constantly changes? As a store owner, we want our currency to be boring and stable. We want inflation to happen over the span of years, but cryptocurrencies change week to week and day to day. Now, imagine we're using cryptocurrency to transfer some money to our family in another country. By the time our family withdraws that cryptocurrency to a local currency that they can use to buy food and other necessities, it might be worth a lot less, or hopefully a lot more. But you can't know for sure. Swings of 20, 30, 40% or even more are not uncommon in cryptocurrencies. Because of all this, for most people, the main use of cryptocurrencies right now is as an investment. An investment where you're saying, I'll put some money into this coin because I believe it will be worth more in the future. The value of cryptocurrencies is currently fueled by tons of speculation on future potential, but not too much on current real-world applications. Even worse, cryptocurrencies are sometimes called a greater fool scam because as an investment, it relies on someone else later on buying it from you because they believe it will be worth even more. So that next buyer is, in the context of the scam, a greater fool than you are. But it's probably best not to be a fool at all, right? Okay, we've also looked at how some cryptocurrencies are deflationary. Usually, this is because the total supply of coins is limited or even goes down over time. As the supply of coins goes down, the value of a single coin goes up. When there's fewer coins available, those that still exist are worth more. What this means is that early adopters get rewarded. If the price of the cryptocurrency skyrockets to the moon, those that bought in early will get the most benefit. Deflation rewards the already wealthy with more wealth. The downside is that imagine now cryptocurrencies are used to buy food, homes, and transportation. Deflation means that late adopters, or even kids who are just growing up, who are hoping to buy their first car or first home, won't be able to do so because as the supply of coins has decreased, the currency has gotten more and more expensive. With pretty much any new technology, whether it's cryptocurrency, blockchain, self-driving cars, or anything else, we should always ask ourselves, is the effect that this will have more positive or more negative? It's not always clear, but it's a question that's worth continually exploring. Finally, with cryptocurrencies, there's no safety net, no protections in case we make a mistake. Remember how blockchain uses addresses for transactions? Imagine we're sending $1,000 worth of Bitcoin to a friend, Daniel. Daniel is a big fan of the world of crypto. So he sends us this long wallet address, which we carefully type into our computer. But it turns out we made a typo. We wrote 7 instead of 8. This simple typo won't be caught at any stage of the transaction. Daniel won't ever get our $1,000 of Bitcoin, and we'll never be able to recover it. If we had used a traditional bank, chances are we'd somehow be able to get that money back. Let's imagine another scenario. This time, Daniel sends us a long address, but we make sure this time to copy and paste exactly that address. But it turns out that the address he sent us was for another blockchain network, something like Dogecoin or even Ethereum. Because we thought that this was a Bitcoin address and we got the network wrong, we'll never be able to recover that money. It's become impossible to access. So whenever you're making a transfer, please make sure you double and triple check the address. Make sure that the network matches between the sender and the receiver as well. In fact, it's important to be aware of all the specific rules of the blockchain network that you're using. These rules aren't always clear to beginners, and if you make a mistake, there's no going back. These kinds of mistakes happen a lot. It's common to see posts on message boards asking questions like, did I just lose $500,000 just because of some misunderstanding? This happens even to early adopters and enthusiasts. Because the blockchain ecosystem is evolving so quickly, it's hard to keep up. There's new developments each day. So it pays to be very, very careful because blockchains are very strict about following the rules to the letter. And they're very unforgiving of any mistakes. All right, This has been a pretty long video, and there's many other criticisms of blockchains like their energy use that we've either already mentioned or will talk about in future videos. For now, you should have a much better understanding of the common criticisms of cryptocurrencies, and hopefully you can avoid sending $500,000 to the wrong wallet address. All right, I'll see you in the next one. Bye-bye. Welcome back. This is a good one. Beyond just cryptocurrency, what's blockchain actually good for? What real-life problems can it solve? Finally, we can talk about something beyond just money and digital currency. Remember, cryptocurrencies are just one of the many applications of the blockchain, introduced way back when Bitcoin was released in 2008. But Ethereum introduced something groundbreaking. We could now store just about any data on the blockchain, including code, these smart contracts that could be run automatically by the computers on the blockchain network. Along with cryptocurrency, smart contracts are the most important concept in the world of Web3. So why are they called smart contracts? That's a bit of an unusual name for a computer program, for some code. Well, it's because they're used to automate the execution of some agreement, some contract, in a way where everyone involved will immediately know the outcome of that agreement, without any interpretation or third-party involvement. No lawyers, no banks, and no unnecessary middlemen. When the right conditions are met, they can trigger a series of resulting actions. We've already learned that the code and memory for a smart contract lives on the blockchain at some specific address, and the code executes whenever a transaction is sent to that address. So why do we need them? How are smart contracts different from your average code that runs on your computer or on a server somewhere on the internet? How is a smart contract different from a regular legal contract that we might use when taking a new job or renting a home? Well, legal contracts are written in human languages like English. These languages are ambiguous. Two people can understand the same contract, the same piece of writing, in two completely different ways. Many cases might not be covered by the contract or might be unclear. So they need to be interpreted by lawyers who we pay big money to do this. But what if instead we had a lawyer that never makes mistakes? Imagine a lawyer reading contracts written in a programming language which is precise and always followed to the letter. That's our smart contract. Remember how we could compare smart contracts to a vending machine or a jukebox that plays some music when you insert some coins? In much the same way, smart contracts follow a series of if and then conditions written in this smart contract programming language. For example, issuing a concert ticket if a certain fee is paid. Paid, of course, using a cryptocurrency. We could do all this on the blockchain because it's now evolved to store any kind of data, not just coins and currency, but also things like concert tickets. Better yet, unlike legal contracts written on paper, any conditions in a smart contract are executed automatically. So you don't even need a third party to interpret or enforce it. We've now replaced our lawyer with a machine that never makes mistakes. Okay, that's a little bit scary. Here's a more friendly looking machine to be a bit more inviting. Because smart contracts are actually pretty cool. You see, because the code lives on the blockchain, how decisions are made is completely transparent to everyone. All the rules and all the data that the rules are being applied to can be read by anyone. We can even use existing smart contracts as templates to build our own more complex smart contracts. We no longer need to blindly trust companies like Apple, Microsoft, and Google that they're doing what they claim with the data we give them. Because smart contracts run on the blockchain, they're decentralized. They aren't controlled by any central entity. And they're immutable. So they can't be changed, lost, or tampered with. The challenge is that these smart contracts are programmed by error-prone humans, by programmers. They're vulnerable to bad coding. They will execute imperfect code perfectly. So, say I write a smart contract that doesn't check for a non-zero price before handing out concert tickets. Well, once I publish that smart contract on the blockchain, I won't be able to change it. It'll be easy to exploit for a curious hacker because the code for the smart contract is public. The result? They get free concert tickets. And believe it or not, these kinds of errors where smart contract programmers forget to check basic parameters are very common. Testing code thoroughly is important to maintain the quality of just about any project. But because smart contracts are permanent and immutable once they're deployed, testing them thoroughly is even more important than for your average code. As is checking for errors and making sure that smart contracts are written cleanly so they're readable, to allow other developers to verify that they're doing what they should and that there are no bugs. And before we move on, the other big problem is their rigidity. In the case of disputes or unforeseen scenarios, human flexibility is something that allows us to compromise. Our imperfection at following instructions is actually a good thing. Smart contracts, on the other hand, don't handle exceptions very well, even if everyone agrees that they're warranted. Smart contracts can't consider the spirit with which the contract was written, like a human judge or a lawyer might. Instead, they always apply exactly what it says. They're not truly intelligent because they're following the contract blindly, to the letter. So let's recap. We've talked about a few different things. Smart contracts are executed automatically and with perfect accuracy, unlike traditional legal contracts. They're fully transparent and readable by anyone, so they require no trust. You always know how they work. And they're immutable. They can't be changed or updated in secret. They take advantage of the security and distributed nature of the blockchain, so a very well-written smart contract will be hard to hack. However, smart contracts are written by programmers who make a lot of mistakes. Trust me, I'm a programmer. So we need to make sure to test our smart contracts very carefully, especially because they're always followed to the letter, mistakes included. And that's our overview of the benefits and challenges of smart contracts. But it's about time we get into the specifics. Welcome back. Smart contracts are great because they're smart enough to automatically deal with all the aspects of a contract. They enforce the contract, they manage it, and they even handle payment. This is a powerful idea, at least in theory. But what can we use it for in real life? Imagine a world where we have full transparency on how every application works. You log into your bank and you see that you're approved for a loan of $5,000. Perfect for buying that first car that you've always dreamed of. Well, maybe. Whatever your decision ends up being on that car, on your bank's website, you'll be able to see your credit rating, exactly how that credit rating was calculated, and how it affected the amount of your loan. Except that's not currently how things work. These calculations are all kept secret by your bank and by the credit agency which determines your credit rating. In some countries, the formulas used are starting to be made public, but these are often only approximations because banks tend to use their own formulas that aren't public. Now, if credit was calculated using a smart contract, you would be aware of exactly how everything you do affects your credit rating. You could make more informed decisions not to do something that will have a negative effect on it. And you no longer need to blindly trust the neutrality or objectivity of your bank. That would be nice, right? Or imagine you're renting an apartment in the city. You sign a legal contract with the landlord, you make your payments, and they hand you the keys to your apartment. Remember how a contract is basically a series of if and then statements. When renting, the contract says, if I pay my landlord a rent of, say, $2,000 a month, then they let me live in my apartment. The trouble with that is, there can be misunderstandings. There might be problems sending or receiving that rent money. Maybe the amount of the rent changed. To resolve such arguments with the landlord, we might need to wait a long time or hire expensive lawyers to enforce our contract. It's a headache. But if our rental agreement was a smart contract, it would execute automatically. The landlord doesn't need to collect rent. The contract itself would know if the money was sent. We could even have a digital lock on the door of our apartment. The lock could be opened with an encrypted code that lives on the blockchain. Encrypted, of course, because we don't want just any random person to look up that code and be able to open up our front door. So now, if I paid my rent, I'll be able to open the front door. But if I miss a payment, I could automatically be locked out. Pretty crazy, right? This is where it would be nice to have a truly intelligent smart contract that can handle circumstances outside of my control. In other words, the smart contract should be able to handle reasonable exceptions, just like a human would. Here's a good one. You could have a social network run on the blockchain, where you share news without a centralized corporation controlling it. The process of how exactly a new article reaches the top of your newsfeed would be transparent. You could even potentially participate in that decision-making process. Maybe you want to see the articles that were voted highest by users in your circle of friends. Or maybe you want a completely uncensored view of what's being posted around the world. This could be important if you're worried about censorship. One often discussed case of censorship is the block of Wikipedia in the country of Turkey between 2017 and 2020. Turkish authorities blocked access to Wikipedia because it contained articles saying that Turkey was involved with terrorist organizations in the Syrian civil war. During this ban, Wikipedia articles could only be read using a VPN service which encrypts your internet traffic. But there was another workaround. It involved hosting Wikipedia articles on a distributed hosting service called IPFS, which we'll learn later is closely related to the idea of the blockchain. But a completely uncensored social network could have its downsides as well. Illegal material could be posted without consequences. Fake news could be spread and voted up to the top of your newsfeed by bots or malicious users. Again, it seems like we'd need some form of moderation for any such application. So, can we build applications that are censorship resistant, immutable, but also that protect users from illegal material? It's an interesting balancing act. And having cryptocurrency, the blockchain, and smart contracts all linked together could be a good thing or a bad thing, depending on how you look at it. For example, you could create a publishing platform, something like Medium, where you can monetize your posts, articles, and videos using cryptocurrency. Or you could create a marketplace for digital artwork. There's so many different possibilities. And don't worry, we'll talk more about these applications. But not every possible application of blockchain and smart contracts is a good idea. We'll learn more in the next video. Let's keep it going. Welcome back. Healthcare is one application of the blockchain that's been talked about a lot. But does it actually make sense to use blockchain for healthcare? Imagine we want to store the medical records for every patient of a hospital, or even a network of hospitals, or perhaps an entire country. It's reasonable to say that we would want these records to be distributed, so they're always available. Blockchain could give us that. And we may want our medical records to be connected to each other, so that a doctor has access to your health history regardless of which hospital you go to, whether you get hurt at home or in a neighboring city or even another country. If your doctor has a good background on your health, your previous issues, health risks, even previous test results, it's likely you'll get better care and a better outcome. This is the future of healthcare, and these things are being worked on. However, we can accomplish all of them with or without the blockchain. So, should we use the blockchain for healthcare? Whenever we adopt a new technology, we need to ask, is it helping us to solve the problem, or is it just introducing more new problems? To protect patients, healthcare is an industry that has regulation, like HIPAA in the United States. HIPAA talks about the rights of healthcare patients when it comes to the security and privacy of their health information. You see, privacy is one of the most important features of any healthcare system. We want our doctor to have access to read and write to our medical records, but not just some random person off the street. Our data needs to be protected. Now, one approach could be to encrypt our data and save that on the blockchain. But that also means it's easy to permanently lose access to all your health records, just like you can permanently lose access to some Bitcoin if you send it to the wrong wallet address, or if you lose the key to your wallet, which is that secret that allows you and only you to access all of your cryptocurrency. And it's not just privacy that's a concern. If a doctor makes a mistake or someone adds a false medical record, we want to be able to revert it. to undo that mistake. In fact, some countries have very specific laws around how medical records are stored, accessed, and managed. In a decentralized blockchain, our data can live on any computer in the network. It introduces many challenges around who's accessing our data and where it lives. One example of such regulation is GDPR, which specifies that patients and basically all internet users have the right for their data to be forgotten, or in other words, deleted. This seems a bit incompatible with blockchain's immutability. And going back to patients' security, well, if it's the patient who controls access to their medical records, then every patient is now individually responsible for keeping their data secure. Their personal machines are very likely more vulnerable to hackers than a hospital might be. And managing your own security on the blockchain is a lot to consider. Just imagine someone who's aging or who may be sick having to worry about the security of their health data. For these people, we want things to be easier and not more complicated. Any blockchain application for healthcare would need to build a friendly user experience on top of the currently very unforgiving blockchain ecosystem. Now, one positive aspect of all the attention being paid to blockchain for healthcare has been renewed interest in improving healthcare systems. Discussion around regulation, security, access to patient data, and using technology for better patient outcomes. Blockchain could be the solution to some of these problems. Maybe it's tracking disease outbreaks or tracking availability of medicine. And it's not that it's impossible to implement an effective medical record system with the blockchain. With enough investment and improvements, it might just happen. But is it easier than it would be with other technologies? My feeling is that using the blockchain is working against us rather than for us. The main advantage is all the extra attention that blockchain brings whenever it's mentioned. And this same criticism could apply to many of the applications of the blockchain, but it's particularly relevant when we have very limited resources, like in healthcare. Even more importantly, lives are at stake. I'll see you in the next video. Welcome back. In this video, we're going to talk about transparency, open source, and we're going to start building up knowledge, which we'll then use to understand something really exciting: decentralized applications. All right, so with smart contracts, we could build social media platforms, more transparent banking, or even games. But in all these applications, what does it really mean when we say a smart contract is transparent? Well, anyone can look at the blockchain and see the code for that smart contract. You should be able to use the data on the blockchain and the code of the smart contract to predict exactly how it will execute. But that's only the beginning of the story. Say we have an open world role-playing game. Let's call it Zelda. And Zelda's game logic is built with a smart contract. Like with most games, there might be some randomness built into our contract code, our game code. You might, for example, want each player's starting location to be random. But if Zelda is implemented using a smart contract, you'll know exactly how that randomized process works. That's not always clear for games implemented traditionally, games that use a client-server architecture. When we say that an application has a client-server architecture, we're saying that the application has a front end. In the case of our game, that would be the game interface that the player interacts with, and which shows them what's happening in the game world. But all the game logic is happening on the server side, on a computer, a machine that's closed off from the rest of the world. That server keeps track of which items every character owns, what level their skills are, and how far they've progressed in the game. The client, that front end that every player sees, talks with this server to get the player's progress. How? Using an API, or Application Programming Interface. An API is basically just a list of data that the player can request from the server, and the actions that they're allowed to perform. It's the language that the client and the server use to communicate. So if the client asks the server a question, say, which items does my player currently own? The server can respond back saying that the player owns a sword, or maybe it's a long list of items. But the exact inner workings of what happens when you send a message to the server, to that API, and how it responds back is hidden away. It's opaque and not transparent. Only the developers who set up that server know exactly how it works. No one else. All right, so what does any of this have to do with blockchain? Bear with me here for just a second. Have you heard of open source software? Open source is a movement, a philosophy where programmers share their code and their applications publicly so that other programmers can reuse that code and learn from it. Open source code is made public so that we can take advantage of the hard work of all the developers that came before us, so that we can focus only on solving the problems that are unique to what we're trying to do. It's a beautiful thing that saves developers a lot of time and already many years ago was saving consumers, the users of our applications, billions and billions of dollars. That's because there's a lot of open source software out there, where any programmer can read the code for that software and know exactly how it works. So here's the question. Does that mean that open source code is transparent, just like our smart contracts? In a way, yes. But smart contracts are even more transparent. They're automatically open source because the code lives on a public blockchain. But, and this is the important part, it's the blockchain network itself that runs that code, and not some private server somewhere on the cloud. A server that's probably owned by a company like Google or Amazon. So, we now have a guarantee that the code that we see is the code that's actually being run. This isn't true for most open source software. Let's look at a silly little example. Say Alice has her own game. We'll call it Sadla. And she publishes Sadla on the internet. It's got a nice website with great graphics and a server that handles all the game logic. Alice then points to a code repository on a website like GitHub saying, "Hey, everyone, this is the code behind my application. It's open source." Now, the question is, does this mean that Alice is being transparent? Well, maybe. You don't know if that's the actual code that she's running. You could run the open source code on your own server to verify that it works the same as the game on Alice's server. But without access to her server, you couldn't be sure. you couldn't know that the code that she shared is exactly what gets executed when you visit her web application, her game. Maybe there's something behind the scenes that works differently. Maybe she's secretly added some code where she tracks every player's actions and analyzes it for their weaknesses, so she can win every time that they play. This is a little bit of a silly example, but the point is, you need to take Alice's word that she's actually being transparent, that the code that she published is the code that's actually being run. Now, smart contracts on the blockchain are much better. Not only do we see the code, but we also know that that's the code that's being run when the smart contract is triggered. Because we can look up that code in the same blocks on the blockchain as the computers that run that code. This all means that applications using smart contracts provide an alternative to what currently exists. Now, users can have control over their data, sharing it in the ways that they want. All of this without trusting some third party, some corporation with its own interests. Very nice. Let's keep it going in the next video. I'll see you then. Welcome back. Decentralized applications. I'm excited for this one. We've learned that any successful application of smart contracts and the blockchain would need a friendly user interface. Depending on what we're trying to accomplish, the user interface could be an application on our phone, a website, or even a virtual reality game. Whatever it is, when we add a front end, a user interface, to a smart contract, we get what we call a decentralized application, or DApp for short. This works a lot like the traditional client-server architecture, except instead of living on a centralized server, the backend for the app lives on the blockchain. The app logic is written into a smart contract, and the blockchain is used for data storage. All the front end has to do is look things up on that blockchain, sending transactions to the smart contract to either read some data or to add some new data. For most dApps today, the front end takes advantage of three very common web technologies: JavaScript, HTML, and CSS. This is what makes up the front-end code, and it's often hosted just like it would be for any website today, on a web server. Maybe it lives on Amazon's web servers, or AWS for short. Maybe it's Google and the Google Cloud Platform. Or maybe it's another hosting service like DigitalOcean. Because all of these are centralized services, any dApp that uses them is only partially decentralized. Sometimes these are called false or fake dApps, but there are better alternatives, like hosting your front end on IPFS, which is decentralized. Again, we'll get into IPFS in a later video. But wherever it's hosted, if we have a web front end, it'll be our web browser that will use JavaScript to talk to the blockchain. JavaScript will interact with whatever smart contracts it needs using an API that can either query the blockchain directly, or it can query someone who knows how to query blockchain. For example, a service that's designed to help us make this process easier. All right, so what is this API that we use to talk to the blockchain? Well, the most common one used to talk to Ethereum in dApps that use JavaScript is appropriately named web3.js. This is an open source project that allows JavaScript to read data from the Ethereum blockchain, or even to send Ethereum transactions. So going back to our diagram, Web3.js would be the API, the language that we use to send and receive messages from Ethereum. But JavaScript and Web3 here are just one common example. The front end for a DApp can be in any programming language, as long as it has some API which can interact with smart contracts on the blockchain. So the result is that a DApp might not look or feel any different from an app that you use today. But the exciting part is what happens behind the scenes. DApps are powered by smart contracts, which means there's no back-end server that we need to manage. We don't need to worry about downtime from crashes. As long as the larger blockchain network is operating, the DApp will be available as well. Even if the team behind the DApp abandoned the project entirely, everyone could still use it. No more worrying about your favorite servers going out of business. So, what's the most popular DApp today? The one that came before all the others. In a way, it was Bitcoin. That's right, Bitcoin was a DApp that allowed users to transfer currency without the need for a centralized organization. It introduced this peer-to-peer digital payment system, the very first DApp. So then, what was the Bitcoin front end? Originally, we interacted with Bitcoin using what was called a Bitcoin client. This then evolved into more usable wallet software and exchanges, where users can buy Bitcoin with dollars, euros, or yen, and can even trade one cryptocurrency for another. You've probably heard of some of these. Two very popular exchanges include the US-based Coinbase and Binance, which was founded in China. But having an entire blockchain dedicated to just one DApp, like in Bitcoin, was very limiting. With Ethereum and smart contracts, this changed. We could now build decentralized applications for whatever we wanted, without all the ridiculously hard work of building a new blockchain specifically for each application. Ethereum became a platform for creating dApps, all using just one blockchain. These days, there's many other blockchains which also allow us to run their own smart contracts, like, for example, Solana. But Ethereum is still the most popular. The challenge is, in Ethereum, the more complex a smart contract gets, the more of these gas fees we have to pay for our transactions. In fact, to break things down, sometimes developers will implement multiple smart contracts for a single dApp. Because of all the required transactions and the potential cost, when building dApps, it's important to spend some time optimizing the cost of your smart contract, making sure it's efficient. And if that's impossible, one approach might be to keep only the most important functions in the smart contract, and later combine them on a server somewhere. The trade-off then is that now our decentralized application becomes less decentralized. So let's look at an example. We could have a dApp which uses two smart contracts, each with a different responsibility. Maybe one tracks which items a player owns, and one keeps track of some game logic. We'd then have a front end, which communicates with a single server. Any requests then go from the front end to the server, which then collects data from both the smart contracts, combines the results, and sends them back to the front end. Is this a decentralized application? Well, the contracts would be decentralized because they live on the decentralized blockchain. But the server would be centralized. And depending on how it's hosted, the front end might be centralized or decentralized. This is just one possible scenario where our DApp is a little bit more complicated and isn't quite centralized or decentralized. This kind of hybrid approach is closer to the reality of most DApps that exist today. But if we can actually get the backend logic to fully live on the blockchain, we get to benefit from all those blockchain superpowers. Being free from censorship, being closely integrated with cryptocurrency and payments, not having to worry about downtime. These are just some possible benefits. DApps are being invested in because the issues they deal with, like privacy, centralization, and censorship, are very relevant to modern times. They have the potential to change the standard for how applications on the web work. If more and more applications start moving to the blockchain, companies want to be prepared. In a way, the hype reinforces itself, for better or for worse. I'll see you in the next one. Welcome back. We've mentioned it a few times already, so let's get down to it. What is IPFS? It stands for Interplanetary File System. It's a way of hosting and sharing files, a file system. And interplanetary is just a grand and fancy way of saying that it's distributed, just like the blockchain. Except it is a little bit different. Users can host and receive files without relying on a centralized server. Users share files with their peers, with other users in a peer-to-peer network. And each file is hashed. Remember, a hash is a unique fingerprint for a file. Every file you create will have a different hash, and if anything about that file changes, it gets a new hash. We say that IPFS is content addressable because the hash uniquely identifies a file, that is, a piece of content. It's comparable to how a street address uniquely identifies the location of a house or a building on a street. So, using its hash, you can look up any file from any computer participating in IPFS. One interesting benefit of this is that if two people create the same file and share it on IPFS, both files will have the same hash and the file will only be created once. So it's efficient. It avoids unnecessary duplication of files. But how is IPFS different from the blockchain? Unlike a blockchain, it stores files and not blocks. There's no fancy consensus like proof of work or proof of stake, and we definitely can't run smart contracts. Its purpose is very different from the blockchain. Instead of tracking transactions, it's used for data storage. The goal of IPFS is to become the main way of accessing the web, replacing HTTP, which is the way we get access to most websites in Web 2.0. So why would Web 3 use IPFS? Well, it allows us to host images, videos, websites, or any other data without having to rely on a centralized host. Imagine we have a DApp with two smart contracts living on the blockchain. This is our back end. We could now host our front end on IPFS and have that front end communicate with those contracts just like before. This would give us a fully decentralized application. Both our contracts are decentralized, and now our front end is as well. This means our entire application will always be available. It'll be free from downtime, censorship from the hosting platform, and so on. But now you might be asking, why not just store our files directly on the blockchain along with our smart contracts? Why not have the front-end code, the website, live on the blockchain as well? Well, due to high transaction costs, the blockchain isn't very good at storing large amounts of data. Think large images or even videos. Because of this, blockchains don't store this kind of bulky data. Instead, whenever it's necessary, a blockchain can keep track of a link to a file that lives on a decentralized platform like IPFS. We say that this kind of data lives off-chain because it lives outside the boundaries of the blockchain. This is in contrast to on-chain data. It's important to realize that none of this is magic. Your file still needs to be saved on a hard drive somewhere, on a machine that's connected to the internet. And you still need to be able to look up where your file lives among all those different machines. Because we're dealing with potentially large files, not every node can have every file. So in case a node doesn't have your file, it'll just point you to the machine that does have your file. But there's a catch. A node on IPFS will sometimes host only the metadata for your file, and the file itself will live elsewhere. The metadata includes things like the hash of the file and where it lives. But the actual file data will still need to be looked up, yet again, somewhere else entirely. It could be on another distributed system, something like Filecoin. Filecoin was created by the developers of IPFS, but its specific purpose was to ensure that files are always hosted somewhere and that they're always available. It does this by paying users to rent their unused hard drive space. The idea to increase participation and keep required files around. So IPFS could take advantage of this, but it might also be set up to look for files on a centralized system, something like Amazon Web Services. So IPFS is not a silver bullet. It doesn't magically solve our problems, and how decentralized it is depends on exactly how it's being used. But it's still a very interesting technology that brings us a large step closer to a decentralized web. Remember that ban of Wikipedia in Turkey? IPFS was used to host a mirror copy of Wikipedia, allowing access despite the ban. Another case was the 2017 independence movement in Catalonia. The disagreement there centered around whether Catalonia should be a part of Spain or be allowed to be independent. The vote for independence was deemed illegal by the government of Spain, and related websites were blocked. However, mirrored copies of these sites lived on in IPFS, allowing uncensored access. So IPFS has already played a real part in not just the history of the web, but the history of the world. And it's another important piece of the Web3 puzzle. In the next video, we'll learn about one of the most talked about uses of IPFS, which is storing NFTs. It'll be a fun one, so I'll see you there. Welcome back. NFTs are possibly the most intensely debated topic in the entire world of blockchain. And not many people can explain exactly what an NFT is. But we now have our fundamentals in place. So let's understand exactly what NFTs are and how they work. Imagine a smart contract whose main purpose is to create objects called tokens. It saves these tokens on the blockchain and manages them as they're transferred from one user to another. This is how NFTs work. The tokens being created by this kind of smart contract are called NFTs. And the process of creating an NFT is called minting. To be clear, that's minting and not mining. We mint NFTs, but we mine Bitcoin. Let's not get those two confused. All right, so why NFT? It stands for non-fungible token. They have a special property, non-fungibility. But fungibility isn't exactly a common word. So what does it mean? An item is fungible when you're able to replace it with another identical item without any change in value or function. For example, coins are fungible items. They're mass-produced and are essentially identical copies of each other. Say we have some 25-cent quarters. Any two quarters are equivalent in function when we're paying for something. So with tokens, two tokens are fungible when we can substitute any one token for another token without any difference in its value or function. We can think of many things this way. For example, food like rice is generally fungible. We don't care which specific grains of rice we get on our plate. We only really care about how much we get and what other food it's combined with, how it's prepared. And a fungible item doesn't have to be a real-world object either. Bitcoins and Ether are also fungible, right? It doesn't really matter which Bitcoin we have as long as it's worth one Bitcoin. Now, NFTs are non-fungible. No two NFTs are identical copies of each other. They're unique. So let's think about this. What are some examples of non-fungible items? Well, a photo of a cool cat is not interchangeable with a photo of a very happy dog. They don't have the same meaning. They're not equal. What else? Well, the same applies to any other artwork. For example, no two paintings are identical. You can have copies or imitations, but the original Mona Lisa is priceless. And it's not just art. Tickets to sports events are usually non-fungible as well. No two tickets are alike. Each ticket is uniquely assigned to your name and to a specific seat in a stadium. A specific seat on a specific date for a specific game. There will be no other ticket like it. In fact, in practice, most real-life items are non-fungible. For example, we can look at shoes. You wouldn't want to trade your sneakers for someone else's sneakers, even if they had the exact same model and size. Even if brand new, they were fungible. So there's an element of subjectivity to fungibility. It depends on how you value two copies of an item. You need to ask, do they have the same function? And do they have the same value to you? That's what matters. Okay, it's time to apply what we've learned here to Web3. I'll see you in the next video. Welcome back. Now that we know all about fungibility, it's time to look at real-life NFTs. We'll find out what exactly does non-fungibility mean for Web3. What do NFTs really look like? And how do we interact with them? With a smart contract, we can create tokens on the blockchain that are non-fungible, just like we discussed. With these tokens, we can represent any non-fungible item digitally on the blockchain. How? Let's look at an actual NFT. What we have here is an image of a kitten. His name is Duke. I'm not making this up. He's part of an NFT collection known as CryptoKitties that blew up in late 2017. CryptoKitties were the first non-financial blockchain application that made it into the mainstream. Even if only for a short while, they generated a lot of interest in NFTs. Why were they so successful? Well, they were both cute and viral. The idea of buying a digital cat for thousands of dollars was so ridiculous that it made a great news story. At their peak in 2018, some CryptoKitties were being sold for hundreds of thousands of dollars apiece. So, how did all of this work? Let's look at Duke's story. Duke was made into an NFT by taking this image and uploading it to Google's cloud servers. At the same time, a token that represents Duke was minted and saved on the blockchain. This token included some data, a series of properties that describe the token. We call this metadata, and it looks something like this. We can see Duke's full name, the address of the image we see above, and a short description. Notice that Duke's image was saved on Google's cloud servers. It lives outside of the blockchain, so we call this an off-chain NFT. Storage.googleapis.com is a centralized hosting service. In case Google's servers go down or someone deletes the image from those servers, the NFT will point to an image that doesn't exist. If that happens, it's unlikely that anyone will ever want to buy this NFT. It'll be worthless. Remember, NFTs are only valuable because people say they're valuable. An NFT that you paid $1 million for will still be worthless if no one is willing to buy it from you. Now, this is where IPFS might come in. With IPFS, our NFT still lives off-chain, but it could now be hosted on a decentralized service with more guarantees that it'll always be available. However, in some cases, even this metadata object we see here is hosted off-chain. This is dangerous because the creator of the NFT likely has access to the server where the metadata is hosted. Think about that. What this means is that the developer can change the metadata whenever they want, even if they've sold the NFT and they're no longer the owner. To prevent this, the ideal scenario would be to store the NFT on-chain with all the metadata and any content, any images living in the blockchain itself. But with Ethereum, for example, even just the cost of storing a few kilobytes of metadata on the blockchain is extremely high. We might be paying more for storage than our CryptoKitty is worth. Because of this, in practice, most NFTs are off-chain NFTs, which means they can be changed. They're not truly immutable. All right, so back to Duke, our CryptoKitty. After being minted and saved on the blockchain, the final step of the process was that Duke's token was sold on an NFT marketplace, a DApp called OpenSea. Someone bought Duke here for about $5 worth of Ether back in 2019. They were the new owner of Duke the CryptoKitty. Now, once the Duke NFT was saved on the blockchain, we need a way of interacting with it. We do this using the same NFT smart contract that was used to mint the NFT. These smart contracts allow us to manage our NFTs and interact with others who also own NFTs. Let's look at some examples. Some actions that our smart contract allows us to perform include transferring tokens that we own to other users. We can use this transfer from function, putting in the address that we're sending the NFT from and the address we're sending the NFT to. And of course, we need to specify which NFT we're talking about, so we can use this token ID that we use to identify every NFT. What else? Well, we can see how many NFTs someone owns by using this balance of function and passing in the owner that we're interested in. We can also look up who owns some specific NFT. So again, we pass in the unique identifier of the NFT to find the owner. And if we're the one who owns the smart contract, we can even mint a brand new NFT, assigning it to any user on the blockchain. We could do this for free, but more likely we'd sell our NFT for some cryptocurrency using a marketplace like OpenSea. Or we could trade it for another NFT. And that's basically how NFTs work. What we see here are all actual operations that we can perform on NFTs today. But there's still something missing. Why? Why do we need all of this? What's the point? Let's find out in the next video. I'll see you there. Welcome back. What's the point of NFTs? Are they a good idea? Let's jump right into it. Here's the big idea behind NFTs. Ready for it? They allow us to represent non-fungible items digitally as tokens. Because of this, they can be used to prove ownership of items on the internet. Specifically, they give us ownership of the original copy of an item. We can then buy, sell, and transfer it if we want to give someone else ownership of that original copy. This is an interesting concept because on the internet, we have an unlimited supply of digital things. Anyone can copy just about anything. But do you own what you have? It's nearly impossible to prove that you're the original owner of something unique. But with NFTs, things change. Let's imagine a viral video posted online. Say it's a video of our trip to an amusement park. We record ourselves going on a roller coaster. By chance, we happen to catch someone's phone flying out of their pocket. We post this amazing video online and it explodes, getting attention around the world. And we lose any ability to control what happens with that video. People on the internet can copy that video an infinite amount of times with perfect accuracy. So were you the original owner? How would you prove it? I'll tell you one thing, it wouldn't be easy. Now, let's imagine the same scenario with blockchain. If you made the video an NFT, this is what might happen. You post your video on a decentralized application, say something called NFTtube. This provides a nice user interface to share your videos online. So NFTtube takes your video and uploads it to a decentralized hosting system, something like IPFS. At the same time, a token that represents your video is minted and saved on the blockchain. Specifically, this token is saved to your wallet, to your account on the blockchain, which means that you own it. If you choose, you can now transfer ownership to another wallet. The NFT itself would keep track of the unique properties of your video, and it would track the current owner as well as previous owners if you'd transferred it. In this video scenario, people can make their own recordings of your video, or they can make imitations. But because everyone has access to the blockchain, they can verify that I'm the original owner, the one that first posted it. At least they'll be able to tell that I was the first owner who published it on the blockchain. And this can all be proven using the trail of transactions on the blockchain. Now, there are some potential problems. This isn't a perfect world. You could post someone else's video on NFTTube before they do. And in the context of the blockchain, you'll be the first owner of that video. You'll be the owner of that NFT. If it goes viral, all transactions would point to you being the original owner. As with all blockchain technology, if you enter bad information from the start, the blockchain will base all future transactions off of that bad information. So in a perfect NFT world, all videos ever created would need to be turned into NFTs for this to make sense. If as a video creator you don't use NFTs or the blockchain, someone could copy your art and claim that they're the original owner. But this kind of scam isn't always a problem. It doesn't always matter that you were the first owner ever. If it only matters that you were the first owner of something in a specific context, NFTs are great. Let's look at an example. If you want to be the first owner of some item in a video game like Zelda, as long as Zelda makes NFTs for each item in the game, you'll always know who, in the context of the game, is the owner of every item. You could transfer your NFT items to other players in the game, or even potentially transfer them to another video games that also supports NFTs. Say our game Vikong over here. This could work for any video game that uses the same blockchain as long as it can give meaning to the NFT in the context of their game. This is something pretty exciting that is being worked on in the world of NFTs today. Not just that, but your in-game items would now have real-world value. You could list them on a marketplace, set up an auction, and sell your items for any global cryptocurrency. I'm sure you know some gamers who would love the ability to profit off of all the time that they spend gaming. I know I do. But on the other hand, this also means that games are now no longer about fun. With NFTs, they turn into a job as well. So will gaming become less fun with NFTs? All right, let's look at another possible use case of NFTs. Event tickets. We've seen this one before. There have already been platforms to use NFTs to represent tickets to concerts and sports events. If NFTs can tap into just a portion of the event ticketing market, that's a lot of value. Online event ticketing is worth tens of billions of dollars. And it'll work as long as the person issuing the ticket makes all tickets NFTs. Then, the person validating the tickets knows that, and they can use that information to see who owns a valid ticket by looking it up on the blockchain. This could all happen with the help of a decentralized application. Another common criticism of NFTs is that they're still easy to copy. After all, you can take a screenshot of an image in an NFT or even just download it directly without any problems. And is that copy going to be worth any less than the original? Well, not really. It's identical. But what NFTs give us is the ability to prove that you own the original item. They allow you to trade not the actual item, but the ownership of that item. It's almost like a certificate of authenticity. It says that you own an original copy. Someone might still copy your video or image, but anyone can look up who owns that video on the blockchain by looking at its transactions. All right, now one thing that we still need to answer is why are NFTs so expensive right now? In 2021, a particularly hot year for NFTs, over $41 billion worth of Ether was sent to NFT marketplaces. That's close to the total market for traditional fine art, which was worth about $50 billion. So why is there so much money in the business of NFTs? We've mentioned how they could possibly tap into markets like online ticketing, which are indeed large markets. But that's only part of the story. Imagine you've been holding your Ether since 2015 when it was worth less than $1. NFTs finally give cryptocurrency holders something to do with all that money that they've accumulated. Instead of withdrawing it, they can put it to work by investing it into something like NFTs. In a way, it doesn't even matter if it's a particularly good investment. And it's because of this that there's many scams around NFTs. We've mentioned the greater fool scam, where as long as someone is willing to trade you for it, you could buy worthless assets as long as you know you can sell them to a bigger fool. And almost like a pyramid scheme, the greatest rewards will always go to the earliest adopters. Sometimes, cryptocurrency and NFTs are a pump and dump scam, where someone famous endorses an NFT, putting the weight of their name behind it. This encourages others to buy, which increases the price of that NFT. As soon as the price goes up, they sell their share at a huge profit, and the price crashes for everyone else. So what does this mean for us? Is there a future to NFTs? All of these criticisms are not to say that there are no interesting uses for NFTs. We've talked about online ticketing and games, but even real estate or land can be represented by an NFT, with the NFT taking the place of what's sometimes called the deed to the property. The deed keeps track of who currently owns that land. This is perfect because real estate or land is very much non-fungible. No two places on the planet are identical. Some properties have already been sold for Ether, with the sale being backed by an NFT. For example, one property in Florida sold for 210 ETH in 2022. Although the main use case for all this still seems to be novelty more than functionality, at least for now. And because NFTs are smart contracts, they're programmable. They can evolve over time, or even evolve depending on where and how they're viewed. How? Well, even if the NFT itself is immutable, its code can generate different output depending on certain variables. For example, where the NFT is being viewed from by using its geolocation. Imagine an on-chain NFT, where the image for the NFT uses the SVG format. If you're not familiar, SVG is an image format used online where the image you see is generated by code. This is the code for the Ethereum logo in the SVG format. It tells us what shape to draw by following this path. And the fill here tells us which color to use. There's many more features to SVGs, but the point is you could have an SVG with a globe that rotates to show the country that you're currently in, all inside of an NFT. Pretty cool, right? Or we could have some code that gives royalties, that pays the creator of the NFT whenever it's sold or traded. This is an attractive use case for some artists who are willing to use the blockchain to create a marketplace for their artwork. So are NFTs a good thing or a bad thing? Well, what I can tell you for sure is that the form NFTs live in today is not going to be the form they live in tomorrow. Things will settle, the best ideas will succeed, and the scams and money sinks will fail. As always, we just need to do our research and be careful until things settle down. And on that note, I'll see you in the next video. Welcome back. DAOs, or decentralized autonomous organizations, are another way of using smart contracts. This time, to make decisions and enforce the rules of an organization. In other words, these DAOs are smart contracts that are used to govern an organization. It could be a not-for-profit business, a corporation, or even a government. We can think of them as an effort to replace human-run organizations with more automated organizations, run entirely by code. People still get to vote, but the resulting actions and any ambiguity around those actions is removed. So a DAO is a smart contract, but that alone isn't enough. It's also an autonomous organization. And for that, we need something very important: people, users who are willing to participate in our DAO. Users who are willing to collaborate with others on the internet for a specific cause. The idea is that these users will share ownership of the community or organization. They'll be able to collectively vote on decisions, on any actions that the DAO should take. And they'll generally be anonymous throughout the entire process. The benefit is that there will be no need for centralized leadership because ultimately it's the smart contract that makes the final decision. But how do the members of our DAO vote on decisions? What's the final piece on top of smart contracts and people? We need tokens, something that the people participating in the DAO can use for votes. We call these tokens governance tokens. They live on the blockchain and they're issued to the users of the DAO based on their contributions. Usually, the contribution that matters is how much cryptocurrency they've invested into the DAO. So the people get these governance tokens in exchange for their buy-in. And it's these tokens that are finally fed into the smart contract to affect what decision is made. The smart contract will execute some outcome based on what votes were made with the tokens. Remember, smart contracts are transparent. They're public and tamper-proof. And because the rules of the DAO are determined by a smart contract, they can only be changed by a vote. The idea is very democratic. But how are DAOs actually used? Well, DAOs are smart contracts. And smart contracts can store coins, tokens, or other data. So we can say that DAOs have a built-in treasury. Basically, their own bank account. This is powerful. The applications are endless. For example, users could deposit their money into the DAO, and it would then be used for crowdfunding, making the DAO into a kind of Kickstarter, allowing users to buy into a product to help finance its development. These early investors could then get automatically rewarded with the product through the code in the DAO's smart contract. And if the product fails, they could be guaranteed their money back. Alternatively, the DAO could be used directly as an investment platform, where users can put money into the DAO and then get returns based on the investments made by that DAO. This could potentially replace banks, brokerages, and even investment firms. But things can get even more interesting. The money doesn't have to go back directly to the investors. It could be used to fund any cause supported by the DAO. It could serve the public good, collecting donations from anyone around the world. The members of the DAO could then collectively decide on how those donations should best be spent. No one could spend any money without the group's approval. A truly transparent charity. Or you could imagine a DAO with employees. Employees that could be paid automatically using the treasury and the code in the smart contract. But DAOs are as much about decision making as they are about money. Let's take a look at an example. In a typical organization, say a corporation like Apple, things are generally very hierarchical. Most decisions come from the very top of the organization, from the CEO or other executives, maybe the board of directors. Sometimes shareholders can vote on decisions as well, where shareholders are anyone who's bought in to the business with their own money, anyone who owns shares of the company. But when shareholders vote on how the corporation should act, the votes are tallied manually. Everything is done by people on the inside of the corporation, usually with the minimal level of transparency required to keep those shareholders happy. And of course, anything to follow the laws where the business operates. Now, unlike a typical corporation, which is managed by humans, a DAO is managed by a smart contract, or potentially a combination of humans and a smart contract. There's no need for special roles like CEO. All members are effectively shareholders in the DAO. And just like a corporation, they have the ability to vote on decisions. But this time, votes are counted automatically, and their outcome is implemented automatically as well. Any funds are held in a smart contract that acts according to the rules of the DAO. All of this is public information. No corruption, no decisions behind closed doors, and no saying one thing and doing something completely different. Sounds nice, right? The reality is that many, if not most DAOs that exist today aren't true DAOs. A true DAO must always have these three things: a smart contract, the collaborating members, and a governance token, a voting system. But especially in the early stages, it's very common to have only the people collaborating potentially on a Discord group. But there's no governance token and no smart contract. These things are often promised in some distant roadmap, but they're never delivered upon. And that doesn't stop the DAO from taking lots of investments or gathering a lot of support from its members. These kinds of DAOs are just traditional human organizations, without any of the extra transparency that smart contracts and token-based voting provide. And because they claim to be real DAOs, there's already an element of deception. But we can't completely dismiss an idea based on a few bad players. DAOs with governance tokens and smart contracts do exist. And it'll take a while for the implementation of these ideas to be perfected, but overall, DAOs aim to take the developments in Web3 and move them beyond just the technology space. DAOs could possibly become an important part of society, of businesses and government, and much more. They're not just an imaginary construct. They're very real things. In fact, in some parts of the world, like Vermont in the United States, you can now register a DAO with the government like you would any other business. And this is just the start. Who knows what will happen next? I'll see you in the next one. Bye-bye. Welcome back. DAOs are fair and democratic in nature, at least in theory. But how do they work in practice? If they're so democratic, then how do members of a DAO vote? Well, one widely used option is to use snapshot.org, a decentralized voting system. This saves us from having to send costly transactions on the blockchain when we want to vote with our governance tokens. Instead, members of our DAO can vote on the snapshot site we see here, which is hosted on IPFS. Let's use Snapshot to take a closer look at a real-life DAO. We'll look at ENS for the Ethereum naming system, or the Ethereum naming service. This is a project that allows us to name addresses on the Ethereum blockchain, so they're more easily accessible. If you've ever seen addresses like vitalik.eth, you're seeing an address on the Ethereum naming service. This is basically the blockchain equivalent of the domain name system, or DNS, which we use to give names like google.com when we're browsing websites. DNS makes websites easier to look up, while ENS makes Ethereum addresses easier to look up. That's what it does. But what does the ENS DAO look like? Here on the Snapshot site, we can see how many members are participating, we can see a list of proposals, and we can learn a little bit more about how the DAO is structured. We can see it's on the Ethereum network, and we can see this proposal threshold, which lists that 10,000 ENS tokens are required for any user to make a new proposal. ENS tokens are the governance token used by the ENS DAO. And we can see a list of voting strategies. These are what determine how the votes are counted. For example, ERC20 votes tracks your voting power by the amount of tokens you have, while also protecting against double voting. While with the delegation strategy, members can delegate their votes to another member. That is, they can allow another member to vote with their tokens. This could be useful if you're a passive investor in the DAO and you trust that someone else will vote for your vision of the DAO. So these two strategies define how votes work for Ethereum's naming service, at least as of the recording of this video. But there's many other possibilities. Maybe you only want to allow certain members to vote. You can restrict who votes using an allow list. Or maybe you want to allow members to vote with their NFTs. That's possible too. There's hundreds of possible voting strategies. Now, if we scroll down, we can see that there's actually some special rules, which is a bit different from what we expect in a DAO, where every voter is supposed to be equal and there's no hierarchy. But it turns out that in practice, some human management can be helpful. Admins can archive proposals and edit various settings, while authors can post proposals regardless of how many tokens they own. Now, we can also browse to the Twitter account for this DAO or the GitHub page for the DAO, where we can see that members can get support and hang out on the Discord channel. So there's definitely a community. There's definitely people in the DAO. And if we look down, we can also see that there's governance tokens, those ENS tokens we just saw, and of course that they use Snapshot to vote on decision-making proposals for the DAO. The only thing not described here is the smart contract, which for the naming service just keeps track of the list of all domains. Those names like vitalik.eth. That's a domain. And the smart contract also tracks the owner of each domain and where it should point. So the functionality for the ENS DAO is automated in that smart contract just like we expect. all the criteria for a DAO are met. Very nice. Now, what would a proposal look like? What are people actually voting on? We can go to the proposals page here, and let's scroll down to this third proposal here, where we can see a detailed description of what's being voted on and some important information: when the vote happened, what kinds of voting strategies were used, and even where the proposal lives on IPFS. Of course, the most important thing is the results. 92% of votes were for the proposal. About 7% abstained from voting, and only 0.02 were against. This proposal passed easily. Counting up the tokens made that very clear. So with DAOs, we vote with our tokens, which we can buy with cryptocurrency. And using platforms like Snapshot, we can do all this using transparent, decentralized technologies. But I want to stress one big potential downfall. Ultimately, voting with tokens blurs the lines between how much you own and your power to make decisions. The risk with this is that it turns the web into a plutocracy where the rich govern and the poor are powerless. Unless you're part of the ruling elite, this probably doesn't sound very desirable. This is something to watch out for in the future. But until then, we can look at how DAOs have been used so far. Historically, what mistakes have been made? To find out, let's dive into one famous DAO that failed horribly. This'll be a good one, so I'll see you there. Welcome back. The DAO was an early DAO created back in 2016. This was its logo, and it was created by a German startup whose other product was a decentralized version of Airbnb, where users could rent out things like cars, boats, and apartments. The DAO promised to invest its users' money. It raised $150 million in Ether from more than 10,000 investors. It was wildly successful, beyond any expectations. At the time, Ether was worth only $20, so $150 million of Ether was a huge amount of the total Ether available on the blockchain. But something went wrong. There were security issues with the smart contract used by the DAO. The code wasn't secured, and an unknown hacker figured out how to transfer money from the DAO's account. They started draining all the money that investors had poured into the account. Only about a month after the funds were raised, the attacker had stolen more than 3.6 million Ether, the equivalent of more than $50 million at the time. DAOs were supposed to remove the need to trust humans, but the programmers who made them were still human, and the code was imperfect. The price of Ether dropped from about $20 to $13. The price crashed by over 35%. Users were starting to lose confidence in the security of blockchain technology. This is the risk of deploying a smart contract like it's just another piece of code. In programming, we often say that it's better to fail fast and fail often, and it's a good way of quickly learning from our mistakes. But smart contracts are much more unforgiving. If a security issue is found, you can't change the rules. You can't revert the database to before it was hacked. So what ended up happening with Ethereum? Because of the massive sum of money involved, the Ethereum community held a vote. 85% of the votes agreed that although everything happened as intended by the smart contract, it was following its broken code correctly, But it still wasn't right for someone to steal all this money. The community effectively decided to rescue or bail out the investors of the DAO. But remember, the blockchain is immutable, and the hacker's transaction was already complete. So what did they do? They created a new blockchain where the hacked money was given back to the investors. They did what's called a hard fork of the Ethereum blockchain. So how did they do it? Is everything we knew about the blockchain being immutable a lie? Well, no. In this incident, Ethereum didn't actually change any transaction history. Instead, a new blockchain was created. The only difference was, in the new blockchain, the funds from the DAO's accounts were moved to a new smart contract. A smart contract with only one function. Its only purpose was to let participants in the DAO withdraw their Ether from that smart contract. They could now get their money back. The minority of users who disagreed with this move stuck to the Ethereum blockchain before it was altered, the one still including the hacked transactions. That's what we now call Ethereum Classic, or ETC. This is the original Ethereum. But the Ethereum we now know and use is ETH. It wiped out the damage that the hacker had done. But it wasn't easy. We'll learn all about forks and what they mean for the blockchain in the next video. I'll see you there. Welcome back. So what's all this fork business? Earlier, we learned that a blockchain is basically a database of transactions that's distributed on many machines around the world. The state of this database is shared by every machine that's participating. This current state is a single global truth, which everyone needs to accept. Having multiple true states would ruin the whole idea, because it would be impossible to decide which transactions are valid or who owns what. It would be chaos. But sometimes the blockchain does temporarily diverge into two potential paths, each with different current states. This is called a fork. Normally, we resolve a potential fork with the help of distributed consensus, using approaches like proof of work and proof of stake. With these approaches, the true blockchain is just the one with the most blocks, the one that's had the most validation work done, and any other potential fork is ignored. We're left with what we call the canonical blockchain. But here's the thing. What if a fork is actually what we want? What if we intentionally want to fork? We've already seen one scenario where this could happen. If a hacker steals a large amount of coins, we might want to undo the hacker's transactions. In other words, something went critically wrong and we want to fix it. This is one of two main scenarios where we might want to fork. The other scenario is actually more likely. This is where we're not changing the past, but instead we just want to upgrade the blockchain. You see, for most software, whenever an upgrade is needed, traditionally the company behind that software will just release a new version and the end user can choose to upgrade or not. But in blockchain, there's no central ownership, no company to release that upgrade. So, for example, with Ethereum, when the Ethereum developers release an update, it's up to each Ethereum client, each node, to update their software to the new version. If some nodes don't upgrade, we may get a split in the blockchain network. New blocks might be produced using the old rules or the new upgraded ones. Usually, this kind of split is resolved quickly, and everyone ends up upgrading to the latest version. But if there's disagreement over some changes, the network might permanently split. This is what we saw with the DAO. Ethereum was forked forever. We got Ethereum and we got Ethereum Classic. Depending on who you ask, both represent the true state of the blockchain. They're both canonical. Now, there's two different types of forks. We have soft forks and hard forks. Let's start from soft forks. These create a new, upgraded blockchain that's backwards compatible with the previous version. So machines on the old version of the blockchain still see the new version as valid. Maybe it just has some extra features. With a soft fork, the old nodes are very likely to eventually upgrade and will end up with one canonical blockchain. But in practice, when we need to make a change, we almost always want to use a hard fork. This is a more radical upgrade, where the new upgraded blockchain completely diverges from the old one. Usually with hard forks, the old version of the blockchain is quickly forgotten about and the new version takes over. But sometimes, like with the DAO fork, both versions stick around. Machines using Ethereum Classic no longer see the latest version of Ethereum as valid. Likewise, machines running Ethereum no longer recognize Ethereum Classic transactions. Both variants of the blockchain need to be maintained separately. Any validator needs to choose which one they're going to support and contribute to. Although some do choose to split their resources and support both forks. At least for a while, until the dust settles and it becomes clear which fork is going to be more widely accepted. So what do we want to take away from this video? Forks are very useful for when we want to upgrade our blockchain. In fact, they're really our only option. Ethereum, for example, has gone through many forks and upgrades over the years since it was released. Not just the DAO fork that we discussed earlier, but also forks to make it more efficient. For example, optimizing the amount of gas that certain actions cost. Maybe it's removing certain limitations, like the ability to interact with addresses that haven't been created yet. Or possibly even adding new features, like slowly moving away from proof of work to proof of stake. For these changes, Ethereum uses a process called Ethereum Improvement Proposals, or EIPs. These ensure that the developers of the blockchain agree that the changes make sense. The EIP process is based on the same process for Bitcoin. And the Bitcoin process is itself based on how the Python programming language keeps track of proposals for itself. It's a fairly well-proven process, and it's also used to specify exactly which changes will be made. For example, if we scroll down, we have EIP 20, which was the first Ethereum standard for creating tokens on the blockchain. This was Ethereum's first really big step towards supporting NFTs and all kinds of other tokens. Once the changes outlined here are accepted and implemented into the Ethereum code, it's then up to the people running the nodes of the blockchain to decide whether they want to run that upgraded version of Ethereum. If not, they'll ignore the changes and keep running the old software. They make the final call. So the process is, again, in a way, democratic. And we still have an immutable blockchain. All the blocks are immutable. But each node can choose to upgrade to a new version of the blockchain code. Hopefully, It's a version of the code that everyone has mutually agreed to. All right, that's it for forks, and I'll see you in the next video. Welcome back. We can't have a course on Web3 without mentioning the metaverse, can we? So what is the metaverse? It's a term for a virtual reality originally coined in the book Snow Crash. More recently, Mark Zuckerberg and Meta, the company behind Facebook, are jumping onto this idea and building what they call the metaverse. They believe in it so much that they renamed their company from Facebook to Meta. So what do we need to know? The common theme behind these different ideas of the metaverse seems to be this giant worldwide network of 3D virtual worlds. It's a lot like the virtual reality and 3D worlds that we already have for gaming. In fact, the creator of Dogecoin has made the point that metaverse is not actually a big deal. It's basically like the worlds we already have in games like World of Warcraft, Second Life, or even Minecraft. So maybe we shouldn't be losing our minds about any of it? The main difference seems to be that the focus of the metaverse expands to general social interaction and even productivity. For example, Mark Zuckerberg is hoping that we'll all be having work meetings in the metaverse. So what does this mean for Web3? Well, you can think of the metaverse as, among other things, a potential application for NFTs. Each object in the metaverse could be an item that uniquely belongs to you. Or you could have items that belong to your friend that you can trade back and forth between these 3D worlds. This would be one big way of generating revenue and potentially increasing the value of different cryptocurrencies, all within this virtual world that borrows ideas from the world of gaming. In video games, what currently exists in the form of communities, clans, or guilds could be run as decentralized autonomous organizations. That's the idea. These internet monoliths like Meta are investing a lot of money into Web3 and the metaverse. It's a little bit ironic that in a decentralized web, based on ideas of moving power away from centralized institutions, the biggest players are still the same internet giants that we all know. Perhaps with everything on the blockchain, these companies will be a little bit more transparent about what they do. The exact future of the metaverse is uncertain, but it's worth mentioning in a course about Web3. After all, Facebook had a huge effect on the internet. It was one of those big players responsible for making social media a term that everyone understands. These ideas will definitely evolve quickly in the coming years, but it's something to keep an eye out for. That's all for the metaverse, and I'll see you in the next one.